let me make it bigger. Of twinkling lessons learned from a brief history of astronomical scintillation. Maria.
Okay, thank you very much. So a bit of a long title, but so we're going to start with something a little bit different this morning where, excellent. Thank you for the slides. We're going to start with something a little bit different this morning. We're going to start with a bit of a historical talk, kind of following on from what Sarah was talking about this morning, a little bit of the history of sunspots. Now then, we're going to talk about the history of twinkling. So I am a PhD student in radio astronomy, and I've been working with a team doing space weather observations. They are the co-authors on this talk, and it's really through them that I first got interested in this history of how humans have used scintillation as a tool. And so when I say scintillation, I really just mean the twinkling that you see of Sirius here. And just as a reminder, this is caused when a compact object is emitting light that passes through some sort of intervening turbulent medium. In the case of stars, that is the atmosphere, and that causes these variations in amplitude that we see as twinkling with our eye. Now, you might all be wondering, how do we get from that twinkling of stars to the sun and to space weather? And the answer is we're going to go through history. We're going to start with the very early history of optical scintillation. We're then going to move to the modern rediscovery of this phenomenon. And as we do, we're going to move from optical to radio wavelengths. And then we're going to end with scintillation today and how it's used with a particular focus on radio frequencies. So as we do this, we kind of want to be thinking about a few different things. We want to be thinking about how humans have used our understanding of scintillation and tried to explain the phenomenon, as well as how we've just used it for practical applications. We also want to be thinking about what kind of assumptions were built into our current understanding at the time of scintillation and whether these were challenged or held based on new data that we were getting. And as I've already hinted at, this talk is covering many millennia in time, and we're going to cover many thousands of kilometers in space as well. So down on the bottom of that slide there is a little map with a color bar so you can keep track of where we are in space and time. All right, so let's start with the oral traditions in stellar scintillation. So these go back well beyond 2,000 years. We don't actually know the exact dates because they're all oral traditions, but they also span right across the globe. So there's this really nice review of Indigenous astronomy by Dwayne Hamisher from 2019, and I'm working in Australia, so that's where I've focused. And there's this really nice quote we actually have from an Indigenous Australian elder who talks about how if you lay on your back in the middle of the night, you can see all the stars blinking. They're talking. So this is something we see parallels in across many Indigenous cultures. They often use song and story, and they encode their record of this twinkling of stars using the language of human interaction. So we get talking and laughing from various Indigenous peoples in Australia. And then we also get the language of dancing to describe these twinkling stars in both South America and Alaska independently. We also see in a lot of these oral traditions that there was an awareness that this twinkling was caused by wind, by weather phenomena. So this was used as a predictor of bad weather in these cultures. And that's something I want you to keep in mind for later in the talk. So moving on to written traditions now, we actually have the first reference to the twinkling of stars from the ancient Greeks, who are, of course, quite well known for their writings in terms of scientific output. So you may know Aristotle. He's quite a big name in lots of areas of the physical sciences. And he wrote in the De Caelo that the apparent twinkling tus asteras stilbene of the fixed stars and the absence of twinkling of the planets, the planetas mer stilbene. So he wrote that this was the case. There seems to be some kind of some kind of scientific awareness that there's something special about the stars that makes them twinkle as opposed to these other objects, the planets, which don't. But that's about as far as the theory gets. I think more interestingly, if we look about 100 years later, we see again these parallels to other Indigenous astronomy that we saw in the oral traditions. So in this poem by Aratus in about 270 BC, which was written as a manual to farmers, we see him talking about how, often before the coming rains, some star has a darkening disk, a halorna melai nomenan. Later, he also talks about how when the bright light of the stars is dimmed and yet no oppressive clouds press upon them, they suddenly become wavering, amenena, and we should expect a storm. So this is really interesting to me because, again, this looks like a connection between the twinkling, the dimming of the stars, and the power that this has for weather prediction. So this is a nice parallel we have between the first written references to twinkling and the references we have going back many thousands of years in the oral traditions. So just to sum up quickly then, in these early observations of scintillation, we have explanations that are largely divorced from the observations. No one really cared about the theory. They wanted to use these observations for practical purposes. There was also no awareness that you really needed compact sources to see this scintillation. However, it was always used as a tool for weather prediction. So these observations were driven by very practical applications, which is something we will see mirrored again in the modern applications of scintillation later. It's also interesting, I think, that this was noticed independently by several cultural groups right across the world. And I'm sure my list here is not exhaustive. If you do know of others, please do let me know, because it would be really great to build this list out. But let's move on now to a bit more modern science. If we're moving into the modern era, we'll start with the Renaissance. So we have a number of people, again, referencing scintillation in their texts, and they start to think about the theory, but no one gets it quite right. So Leonardo da Vinci thinks that it was in some sort of optical illusion in the eye. A bit later, Tycho Brahe thinks it was intrinsic variability in the stars themselves, and Johannes Kepler actually agrees with him when he discusses observations of the supernova 1604. So all of these gentlemen, extremely smart, extremely thoughtful scientists, but they couldn't quite get the theory right. And I think part of the reason is they were clinging to these old ideas of geometric harmony that were inbuilt to lots of earlier cosmological theories. It was really not until a couple of hundred years later with Sir Isaac Newton that we start to get some accurate descriptions of what is actually causing scintillation. So Newton was the first to realize that it is the air in a perpetual tremor, as may be seen by the twinkling of the fixed stars, but these stars do not twinkle when viewed through telescopes which have large apertures. So not only did Newton get it right that this twinkling is caused by an intervening medium, he also started to realize that there's some sort of dependence on either aperture size or angular size of the source in terms of whether or not we can actually see this scintillation towards any given object. Even so, though, it's not really until the 1950s that I was actually able to find any reference to the angular size of the source in viewing scintillation. And this down here, this paper from Ellison and Seddon in 1952 is the first reference that I could find written down of discussions of scintillation where we know that it's caused by an intervening turbulent medium, and we need very, very compact sources on an angular scale, on an angular size, to be able to see this scintillation. So to sum up then, in ancient times, scintillation was used for weather prediction, and the observations were very forward-looking. They cared about the practical applications. And understanding of the underlying physics was not necessary, and any theoretical discussions that existed were totally separate. When we move into the post-Renaissance period, there was a growing interest in the physics behind scintillation, as well as greater records of observation. But no one quite got this theory right, mainly because they had preconceived theories that were hampering their progress on the theoretical side. So now I want to move into the modern period and look at some other wavelengths and connect this up to the sun and space weather. So now we're going to look at radio frequency scintillation. There are three categories of this scintillation that are just distinguished by the intervening medium. So there's the ionospheric scintillation, which happens on about 10 seconds timescales and is caused, of course, by the ionosphere. There is interplanetary scintillation, which we heard a little bit about yesterday. And this is caused by the solar wind. It happens on second timescales, so it's one of the quickest forms of scintillation we see in the radio. And then the slowest form that we see is the interstellar scintillation, which happens on our timescales and is caused by the galactic medium. So the first of these to be discovered was the scintillation caused by the ionosphere. So this was discovered in 1946 as minute scale variations towards Cygnus A. And you can see those, this is the original data on the slide up here. You can see those as these very quick variations that are modulating the overall interferometric fringes here. And quite soon after this was discovered, it was localized to a theorized point source by Bolton and Stanley, but they weren't actually able to prove that it was coming from a point source. What's interesting, though, is that even though this was discovered quite quickly, there were still competing theories as to its cause. So, oops, I've misspelled Cambridge. That's a bit embarrassing. There were two competing groups here. The Cambridge group thought that this was an intrinsic phenomenon, and that was based on their assumption that it was an analog to sunspots. The Australian group, however, believed this was a local ionospheric effect. And there was a bit of competition between them for about 5 years as they both tried to get more observations to try and prove their theories right. It was not until 1950 when the Cambridge group actually managed to get observations across long baselines and see the decorrelation of this scintillation that they finally agreed with the Australians that we were looking at a local effect caused by the ionosphere. And once they did that, things moved fairly quickly. It was only a year later that we actually got the theory behind the ionospheric scintillation and some more of the physics was explained. So to sum up then, competing Cambridge and Australian groups drove fast progress in the field, especially when you compare this to the centuries it took to get the optical scintillation right of the stars. Cambridge was initially led astray by the similarities with sunspots and the hypothesis that the discrete sources they were looking at were galactic radio stars rather than extragalactic sources. So they were slowed by their preconceived ideas. We'll move on to interplanetary scintillation next, because this was the next one to be discovered. So this was again discovered serendipitously as second long variations towards a number of compact sources. And again, on the slide here, this is really these very exciting early first observations of interplanetary scintillation. Now, this was so serendipitous that it was actually only published as an appendix in the discoverer's thesis. So this was in Margaret Clark's thesis from 1964. And in that thesis, she actually nailed the theory as well. She got it totally correct that this had to happen towards very, very compact sources. There was a strong angular dependence. And she also realized that it had to be the solar corona that was the scattering screen. Now, her supervisor didn't believe her, which is perhaps why it only made it into the appendix of her thesis. And it took another year for him to get extra observations to convince himself that, again, yes, this was an intrinsic effect. And that led to this Nature paper here in 1964. So to sum up now, we're getting very, very quick in terms of the timescales from discovery to explanation. We're really only looking at a year here, which is quite exciting. The final type of scintillation to be discovered was interstellar. Again, we've got very early data of this interstellar scintillation shown in the plot on the left here, this time towards an extragalactic radio source, an AGN. So this was both observed towards galactic pulsars and extragalactic AGN as variations over our timescales. And again, in this case, the extragalactic groups were led a little bit astray because they were really excited by the fact that if this was intrinsic variability, it would have to point to new physics in these extragalactic sources. There was nothing at the time that could explain it. However, fairly early on, there was a correlation discovered between the scintillation and the dispersion measure of the galactic pulsars. So the pulsar people really knew quite early on that this had to be local variability. It was not intrinsic. That said, the groups took a while to talk to each other. So this intrinsic variability realization was published in an IAU colloquium, actually, from 1996. But it is not until 2006 that we get a paper from the AGN group, again, presenting new observations where they were really convinced finally that they too were looking at a local effect from the interstellar medium and not an intrinsic source at the AGN. And just an interesting hangover from that period, the extragalactic astronomers also still refer to this interstellar scintillation as intraday variability in AGN, which is just kind of a hangover from that period where they hoped that it might be intrinsic. So bringing this back around to the sun and space weather, because that's all why we're here. As we heard a little bit yesterday, IPS or interplanetary scintillation can now actually be used as a really nice remote probe of the solar wind. So space weather is, of course, as we all know, now a global effort. And we actually have multiple ground-based observatories that are currently recording IPS measurements to track the heliosphere and identify CMEs in particular. So I've identified many of the observatories up here, and they're shown on the map on the bottom right. In particular, in terms of things we can do with these, we can look at inputting the data into heliospheric models. And Bernie Jackson from UC San Diego is doing lots of really great work in this area. We can also take measurements of the solar wind speed, again, from the ground, which is really nice. It means it's probably less expensive than going to space. We can look at the detection and modeling of CMEs, and we can also detect stream interaction regions coming from coronal holes. So to sum up then, all these 2,000 years, what have we learned? So this observation of scintillation and its use as a tool for prediction has very deep historical roots, as does the theorization and the predictive power of it. There have been similar misconceptions repeated across the fields, particularly concerning whether this was an intrinsic or a local effect, as well as how the aperture and the source size affected our ability to view this twinkling. Ultimately, though, it was really the interaction and competition of modern science groups that really drove rapid progress in the field. So instead of taking centuries to understand this phenomenon like we did for the stars, it took years, or in some cases, less than a year. So if we look at co-adding all of the slides that I had today, we can see that really this is a nice demonstration of global science at its best. We've spanned more than 2,000 years, and we're basically hitting every continent on the map. And more importantly, we've moved quite nicely from weather prediction with stars to space weather prediction in the radio. So I think I'm probably out of time there. I'm just going to leave you with this nice slide showing radio scintillation in action with data from the MWA, as well as a list of the space weather talks focusing on IPS that you can see at the GA these next couple of weeks. Thank you. Thank you so much.
Very interesting talk. Thank you very much. In the back of my mind, I don't work in this, but in the back of my mind, I read a report somewhere from the 1800s about twinkling of stars during the aurora. And I'll have to go and dig it out and try and remember what book I saw it in. But they saw, I think, memory serves me correctly, they saw the twinkling of the stars before the aurora started. And then they saw increased twinkling. But I'll have to dig it out. So it's in the archives in Dunsink Observatory in Dublin, where I work. So I'll definitely drop you a line.
Please, that would be amazing. Thank you very much there. It's a great connection to space weather again.
Exactly. Now
Yeah.
to the atmosphere and space weather and so on.
Yeah, that'd be great. Thank you.
I have one space before one. So ionosphere is.
Sorry, we can't hear you.
People online.
So the ionosphere is pretty reactive medium. So whenever we have an event on the sun and it's coming toward us, is there any signature of the ionosphere before the arrival of CMEs or anything that we can detect in the ionosphere before?
That's a really great question. And I think it's beyond my expertise in this area. But I mean, it sounds like we certainly have records from the past where we can see the stars twinkling, which I guess must be an ionospheric effect if we're seeing optical scintillation. Very great question, though. And I'm going to clearly have to do some more research. Thank you very much.
The next talk is by Yoshita Barua, and he's going to talk about a detailed sun-to-Earth investigation of space weather condition that triggered the loss of the Starlink satellites in February 2022.
Okay, hi everybody. I'm Yoshita Barua from SESI, ISA Kolkata, India. And I'm going to talk about the loss of the Starlink satellites in February 2022 due to a geomagnetic storm and our analysis on this event. To set the context, coronal mass ejections and high-speed streams, which are Earth-directed, have the potential to drive geomagnetic storms on Earth. Now, during a geomagnetic storm, particles are injected into the magnetosphere and eventually into the ionosphere, and they end up constituting a current. Now, we know that the atmosphere is a resistive medium. So naturally, a current that is being driven through the atmosphere generates Joule heating. Now, because of Joule heating of the atmosphere, it expands upwards, or it kind of upwells. So now, if we have a satellite at a certain altitude, it would experience higher atmospheric density around it during a geomagnetic storm than it would do on a quiet day. Now, this is a very familiar drag equation. Now, the drag force is basically a resistive force which the ambient or the surrounding medium exerts on a body that is moving through it. And it depends on the density of the medium. So in case of a satellite, if the density around it, the atmospheric density around it is high, it would face more drag force. Being a resistive force, it basically decelerates the satellite, which is why it loses altitude. To estimate the orbital decay of satellites during this storm, we made use of these particular equations. Basically, we are looking at the change in the semi-major axis of the orbit of the satellite. And so a satellite on any given day undergoes orbital decay, but during a storm, a geomagnetic storm, it is enhanced. So these equations basically give you the contribution of the geomagnetic storm alone on the orbital decay of the satellites. Also, we have made use of a module called the Storm Interaction or STORMY module, which is developed by Shouvik Roy and Dibyendu Nandi, to estimate the current density around Earth due to which is induced by this geomagnetic storm. Now we know Joule heating is proportional to the square of the current density. So in our case, this computation of the current density works as a proxy for the Joule heating that must have been induced by this geomagnetic storm around Earth. Now, SpaceX issued an official update on 8th February where they listed down these particulars. So the Starlink satellites were launched to an altitude, a very low altitude of 210 kilometers orbit on 3rd February 2022 at 1813 UT. But on 4th February, 38 out of the 49 launch satellites started to deorbit. And in a few days, in a matter of a few days, by about 7th February, a lot of them re-entered the atmosphere. Now, following on this update, we tried to look for sources, for eruptive sources that could have generated these geomagnetic storms on Earth. Now, there was an M-class flare from the active region 12936 on 29 January, which was accompanied by a CME. Now, this was an event that was observed and reported by a lot of space weather forecasters around the globe. So this was well known. But this was a surprise. So we went ahead and we found 2 more CMEs on 31st January and 1st February. These were much fainter, these were slower in speeds, and their on-disk signatures were also kind of elusive. And these occurred very close in time, so they must have interacted sometime during their transit towards Earth. Now, these being faint were not, these largely went unnoticed by the community. Also, 2 coronal holes were observed on 2nd February, which are marked in like these orange and blue contours on this image. Now, we know that coronal holes are the sources of high-speed streams, which can, again, drive geomagnetic storms on Earth. Now, this is a very busy plot. This is basically solar wind observations from near Earth. The blue dashed line there marks the launch time of the Starlink satellites. And the last panel in the plot shows the geomagnetic storm intensity in terms of the DST and the KP index. So all in all, we identified 3 CMEs in this plot and high-speed streams in this plot, which is consistent with our observations near Sun. Now you would, a closer look, and also the first CME that hit Earth drove a geomagnetic storm of that peaked at about -66 nanotesla, and subsequent high-speed streams and the 2 other CMEs drove another geomagnetic storm of about -60 nanotesla. Now, these are very modest space weather conditions. We cannot call them extreme by any standards. Now, a closer look at this plot will actually tell you that the Starlink satellites were certainly launched after the passage of the first CME through Earth. But if you look at the DST, the atmosphere still hasn't recovered to its quiet state. So actually, the Starlink satellites were actually launched to a very perturbed atmosphere in the beginning itself. And subsequent hits by the 2 other CMEs and high-speed streams further basically subjected the satellites to a prolonged, disturbed atmosphere. Now, this is another interesting plot. Firstly, we did not have access, so Starlink did not make the accelerometer data public. And we need accelerometer data to calculate the orbital decay of the satellites. But we did have access to accelerometer data from a satellite called Swarm-C, which at the time was flying at about 434 kilometers. So we used this data to compute the orbital decay or estimate the impact of the geomagnetic storm on the satellite. You see that the first panel here shows the current density, the square of the current density induced around the Earth. The second panel here is the thermospheric density at the altitude of the Swarm-C satellite. And you would see that you would see simultaneous increases in the thermospheric density with the current density, which is expected. The third panel shows the orbital decay rate for the Swarm-C satellite. Again, you would see simultaneous increases in the orbital decay rate with the increase in thermospheric density and current density. The fourth panel basically shows the total orbital decay of the Swarm-C satellite, which is about 23 meters for this event. The last panel is quite interesting. So what we did is we created a modeled synthetic ephemeris and we validated it using observations from Swarm-C, and we used it to estimate the orbital decay of the Starlink satellites. The pink and salmon curves in the last panel basically compute the orbital decay of the satellites when they are in an open book configuration. That means they have a minimum RAM area exposed to the surrounding medium. The dark blue and the light blue curves are indicative. So they are the orbital decay curves for the Starlink satellites when they are in an open shark, they are in a shark fin configuration. That is, they have a maximum RAM area of about 4.48 meters square exposed to the surrounding medium. Now we see that for both cases, the orbital decay of the Starlink satellites have been hastened or have been, so there's a faster orbital decay of the satellites during the geomagnetic storm as opposed to what they would have gone through if they were quiet conditions. So, so from this plot, there are two major takeaways. One is the satellites were already launched to a very low Earth orbit, so they were subjected to high drag from the get-go. Point number two is SpaceX, in their update, mentioned that the Starlink satellite started deorbiting and re-entering the Earth on 4th February. Our analysis shows that for a maximum RAM area of the Starlink satellites, they also deorbit to a very dangerously low altitude of 100 kilometers by 4th February. So this is indicative of the fact that the Starlink satellites must have assumed orientations where maximum RAM area was exposed to the surrounding medium quite a few times in the time between 4th February and 7th February, which led to their fast orbital decay. So we went ahead and played around with our synthetic ephemeris a bit more. What we do here is we have now 3 satellites which are similar. One is similar to Swarm-C, the other is similar to a Starlink satellite with a RAM area of 1 meter square. The third is again similar to a Starlink satellite with a RAM area of 4.48 meters square. Now what we do is we initialize them from an altitude of 210 kilometers, which is the initial altitude to which the Starlink satellites were launched, and let them decay under the same atmospheric conditions during the same time frame. And we do that same activity by initializing the orbit again at 434 kilometers, which is the altitude of the Swarm-C satellite initially during this time. For both the cases, we observed that the Starlink satellites, even for a minimum RAM area of 1 meter square, underwent almost 3 times more, like 3 times faster orbital decay than Swarm-C during the same time under the same atmospheric conditions. So what is going on here? We attribute this to something called the ballistic coefficient. Now, ballistic coefficient is a measure that the body is a measure of the resistance that the body offers to a drag force that is subjected on it. So naturally, lower the ballistic coefficient, higher is the impact of drag on the body. Now, for Swarm-C, we have this ballistic coefficient with 668. For Starlink, even for a minimum RAM area of 1 meter square, the ballistic coefficient is almost 3 times lower than that of Swarm-C. So this suggests that a physical attribute of the Starlink satellite in itself was contributing to a faster orbital decay or loss in altitude of the Starlink satellites. So in summary, the Starlink satellites were launched to an already perturbed environment, and subsequent hits by more high-speed streams and coronal mass ejections, again, subjected them to a prolonged, disturbed environment. In addition to space weather events, the Starlink satellites were also launched into a very low orbit, because of which they were exposed to higher than normal drag. And physical attributes of the Starlink satellites, like their low ballistic coefficient, further compromise their ability to survive the geomagnetic storm. So we have published a paper on this, and this is the QR code. You can access it and give it a read. And thank you for your attention. Yes, please.
My question is, well, it's probably addresses your talk, but it's a little bit more general. So science missions are rare and far in between. They are dedicated, and that's what we want. But for the ionosphere in particular, and the Earth atmosphere in general, we have way more commercial platforms out there than obviously science missions. Are there any measurements that these platforms are doing that we can use right away? You can just gather their data. Like, for example, I think you mentioned some examples here in your talk. Or the other thing, are there any easy measurements that we can probably in the future just put a small instrument on these platforms that will give us so much data all over the place around Earth that will help us probably get some insights into the physics of the Earth atmosphere?
Yeah, we did look through a lot for accelerometer data, firstly, to compute the orbital decay. And also accelerometer data can be used to retrieve thermospheric density that the satellite, kind of experiences around it. But then I'm sure these measurements are being made, but they're not made publicly available. We only got it for Swarm C. So we don't have that handy. And secondly, I believe that one of the major uncertainties in computing the orbital decay lies in the thermospheric density. So if we can actually make in situ measurements and sample this density at multiple, at different lattice longs and altitudes, we can probably use them to make better models to be able to predict thermospheric density, and which can aid in computing orbital decays for the satellites. Yeah. Does that? Yeah. Microphone.
One way to sell this to the commercial side is basically the outcome of what we do will be useful to them. That's one way to sell it to them. That way, otherwise they will, as you said, they will not give you the.
You're right. You're right. Yeah.
So, other questions? Yeah. Nariaki and yeah, either one. Please go ahead. Yeah. Yes.
Okay, just figuring if I were working for SpaceX and designing such launches, I would be interested in the probability of such accidents. So what fraction of such launches would be affected?
What fractions of these launches will be affected, is it? I mean, it is very difficult to actually pinpoint, which satellite would actually go down. But we can certainly say that certain satellites at a certain altitude are in danger, and we always have a lookout for space weather events. So using measurements and using certain proxies from them, we can actually run thermospheric models and then do a modeled run for satellites at different altitudes, which is similar to what we did for the Starlink satellites in our case. So yeah.
How can we avoid this kind of accident? Because I just looked at the solar wind data for this period. Nothing very unusual, just a small perturbation, You said already perturbed, but it's not too much.
Yeah, that's right. I think it's important to take into
CME.
That's right. I think it is important to take into account that a prolonged an atmosphere which is disturbed for a very long time can potentially cause more damage to a satellite than one huge blow. Firstly. Secondly, I also believe that they need to pay more attention to space weather forecasters. Yeah.
It's a very important lesson to learn.
Yeah. I think that, okay.
Hi, is that background picture, is that representative of the actual placement of satellites?
It's not the actual, but it's like a cartoon of the Starlink constellation that SpaceX, I think, wants to make. As far as I remember, I picked it up from Google. Yeah. Okay. Thank you very much.
So the next talk is from Emma Peracchioni from Politecnico di Torino in Italy, and she's going to talk about forecasting geoeffective events and evaluating the most predictive features through a new classifier-dependent ranking scheme. Emma.
Okay, so at first, thank you to the organizers who gave me the opportunity to give the talk in this event. And yes, today we will talk about a new classifier dependent ranking scheme, which will be called greedy feature selection. And this new classifier dependent greedy scheme will be used to help in forecasting geoeffective events. Well, just to introduce a bit myself, I'm Emma Perracchione. I'm from the Politecnico di Torino. I have a tenure track position, and currently I'm working with the MIDA group of the University of Genova. And specifically, this group is led by Michele Piana and Anna Maria Massone. Okay. Let's see which kind of data we are considering. Well, we want to predict with, of course, we are in the era of machine learning, so with machine learning tools, if we may have a geoeffective event or not. And in order to do this, so in order to train our machine learning tools, we need, how to go back? Okay, we need a data set, an historical data set. And so we will consider the data set, which is known as Omni, and it is basically data which are sampled in L1, and the satellites that measures the quantities which are listed here are ACE and WIND, and they produce some measurements. So our data set is from 2005 up to 2019, and the measurements that are at our disposal in L1 are the magnetic field intensity, the velocity of the solar wind, and of course, their 3 directions. Then we have the proton and the density number. Finally, beside these quantities, which are measured at L1, we also have at disposal some derived quantities. And those quantities are kinetic, magnetic, and total energy, and the magnetic helicity. Okay, which is our goal? Our goal first is to explore some feature reduction techniques in order to identify among all these variables, which are 15, which are the most predictive one, okay? Because not only in space weather, but each time that you face machine learning, usually you have many features and you want to reduce them, okay? So this is the first goal, to explore several feature selection techniques and to introduce the one that we think is better because it's new and it's dependent on the model that we are going to use to forecast geoeffective events. Then, what is our task? We have all those variables in L1 plus some derived quantities, and we want to predict if we have a geoeffective event or not. Then we introduce this CMH, we also have at disposal this CMH index, which is measured on Earth, and it is an index of the geodisturbance that we may have after an event on the sun. And we label this CMH index, and we say that we have a geoeffective event, that is, the label is +1, if this CMH is less than -50 nanotesla, otherwise we don't have any geoeffective event on the sun. Okay, and as I was saying, we need some feature selection or feature ranking scheme. Well, what is my main concern about feature reduction? Usually in many papers, many authors, and I also did that, we want to reduce the feature, and we typically use a kind of linear lasso regression. It is maybe the most popular one, okay? So you take the feature, you reduce the feature with this lasso selection, and after using a linear model to reduce the high number of features, you take those features and you use highly non-linear models, such as neural networks, feed-forward neural network, long short-term networks, something which is highly complex and highly non-linear. And here is the problem, because if you find some meaningful feature for a linear model, it doesn't mean that such features are really meaningful and predicting when you then use a neural network. So what is our idea? Our idea is to take a tool that comes from approximation theory, which are called the greedy scheme, and adapt them to the context, the modern context of machine learning. And our greedy ranking of the features will be classifier dependent in the sense that if you want to use a given neural network to predict, then with this greedy scheme, you will get exactly the features that you need for that classifier, okay? And let's see briefly how it works. So just a short recap about how it works. Of course, you take your initial data set, which are the labels, Y, and all the data, X. You split it, as always, into train, validation, and test set, and how this greedy selection works. So let us suppose that at the 0 step, we have one feature. Let us say the first one, X0. We already get it. This is the most important feature that can help you in classifying, X0. Then, how we proceed? We want to select another feature after X0, okay? So what we do is to construct many models, D-1, because we have D features, okay? Many models, which are denoted by MP, by taking the other features step by step. What I mean is that we have already selected X0, then I construct a model with X0 and X1, another one with X0, X2, X0, X3, and so on, okay? I evaluate the performances of such models, and then the feature that returns the best performance will be also the most important for that classifier. The classifier is denoted by M, and that is that I will take exactly that feature in my dataset. And we continue in this fashion way until we reach a certain accuracy. So in this way, look, we are selecting for any model M can be anything. Can be a lasso regressor, can be a neural network, can be whatever you want. And for that model, we are selecting iteratively the most important feature. Here, mu is a given score, an accuracy score, and you can think to mu as the TSS or the F1 score, whatever. This algorithm is very flexible. And now you may have realized that, or better, I have to confess that I'm a mathematician. So we will see, and I am a mathematician who likes to prove useless stuff by hands on paper, okay? So now, step by step, we will see the convergence of this algorithm in strange Sobolev and Wasserstein spaces. I'm kidding you, let's see the interesting parts of the results. And here we apply the algorithm to this Omni dataset, which is exactly more or less the datasets, the data sampled by ACE and WIND. And as we can apply any model M, here we explore both supervector machine and feed-forward neural networks, okay? I remind you that we had 15 features at the beginning, and here we have the greedy ranking for both as a supervector machine and the feed-forward neural network. What we can observe? First, some physical observation. We have coherently with the experience that physicians have, we have as most important features something related to the magnetic field, velocity, and energy, at least for the SVM. But we notice that we have just 1, 2, 3, 4, only 5 important features. So with this greedy method, we are able to identify the most and the minimal set of features that we need for making our prediction. And this is even more impressive if we use a feed-forward neural network, because with this greedy scheme, we are able to identify just 3 features which we claim to be more relevant for our task. Okay, and the score that we use in the grid implementation is the TSS, and we decided to use this because we have a really unbalanced data set, so we have really a few positive events, and this score turns out to be quite stable in when we have unbalanced data set. Okay, and now let's see if our greedy selection is good for the prediction, okay? Till now, we have just drastically reduced the number of features in a smart way, let me say. And here we are instead testing, so on unseen events, both the supervector machine and later the feed-forward neural network on unseen examples. Here I reported some metrics, okay? And these are the scores obtained with all features, that is, all the 15 features that we have seen in the first slide. Then, with the feature selected by lasso, which is a linear regressor, and please look that there are 11 features selected by lasso. And in the last column, we have the results of our greedy selection with only 5 features instead of 15 or 11. And what you can observe is that, of course, you have an advantage because you are using less feature in training the models. But at least with the support vector machine, you also have an improvement on all the scores, the accuracy scores. And we think that this is because we are not only selecting the most important feature for the classifier, but it's also because we are neglecting the one that can cause some trouble to the classifier. And in particular, SVM is known to be sensitive. It's a basic tool, so it's known to be sensitive to noise, okay? And this overall improvement is due to the fact that we are somehow keeping out the noise for this estimator. Then we repeated the same with the feed-forward neural network. And again, those are the score, the first column obtained with all features. Then we have the one with 11 features obtained by lasso, which is a linear tool. And in the last column, we have our greedy selection. In this case, we can see that the results are simply comparable. So we don't have any improvement in the accuracy score. The improvement is the fact that we are able to achieve more or less the same accuracy by using just 3 features out of the 15 that we had at the beginning. And the fact that we have less improvement is due to the fact that the neural networks have a more complex structure and they are more robust to noise somehow. Okay. And here is just to give you an idea about the prediction that we are doing. Here is a temporal window, and the task in blue, you can find the SIMH index, and the task was to predict when the SIMH index was below the threshold of minus 50 nanotesla. In the first plot, you can see the prediction with the feed-forward neural network. So this is the one in green. So you have any storm, then the storm, at least this one is correctly detected, that one is correctly detected, and also this one. With support vector machine, we have less accuracy, and this can be seen also by this plot because we are missing this true positive event. Anyway, our classification scores are quite good, and we are able to understand, to predict when a J-effective event occurs or not. And as a work in progress, we are trying to split this binary classification problem in 3 class problems. And so we would like to characterize the beginning, the onset of a geomagnetic storm, the recovery phase, and the last class will be no storm. Okay, with that, I conclude. I just want to acknowledge this project and thank you for your attention.
Yeah, really great talk. Thank you. I just had a question about the features selected by the greedy algorithm. Were they all ones that you would have expected to be the most impactful, or were any surprising?
No, well, I can try to go back to the greedy selection. So here, maybe I was not so clear during the talk. We are trying to predict geomagnetic disturbances 1 hour in advance. And what it means 1 hour in advance, it means that we can use actually the SIMH index measured now to predict something 1 hour in advance. Okay, the talk focused on 1 hour, but we can do better, not just 1 hour. And of course, we are trying to predict not the SIMH, but the label SIMH. And reasonably, this is the most important variable. And in fact, any algorithm for any algorithm, the SIMH was the most important one. Then we were a bit surprised. Okay, we always had the B and V and some of the energies, let's say, and we were a bit surprised about the fact that the magnetic helicity was not in the most important feature. But we are now currently working on that. Well, this study only focuses on geoeffective events, which can be CMEs or high-speed streams or other things. And by focusing only on CMEs, we think that the magnetic helicity should be one of the most relevant features. So that was maybe the only surprise.
Cool, thank you.
Welcome.
Thanks a lot for the talk. That's some great results. I was wondering, so this is something we kind of expect, meaning that feed-forward neural networks or like deeper networks would kind of like catch these, let's say, features and set them apart, underlining, let's say, the ones that are more important rather than the like something simpler that wouldn't do that. So this is like something very useful for like low level machine learning methods, which is very useful. I was wondering how easy is the implementation of your method, meaning is this like a package that your team is trying to publish in order for the community to use, or is it something that is just on the research aspect right now?
Okay, no, this is really a good question. The implementation is trivial. It's on this slide, the implementation itself. This is not currently available because this strategy has some problems of efficiency behind, because each time you have to train a model and another model. So you have 3-4 cycles, which in principle is super easy to implement, but it is not efficient. So before publishing the code, we would like to think to some smart way to construct surrogate models, okay, with many data in order to do the whole procedure. Up to now, we simply took a smaller data set, okay, with the same percentage of positive and negative events. But we would like to see, before making it available to the public, some smarter way to get a surrogate model and to speed up the whole process.
And if I can follow up, what is the loss in efficiency? Meaning, what is the runtime loss? I mean, it's pretty cheap to train low level, not for feed-forward neural networks, but like you know, support vector machines, etc. So, is it in the order of minutes or?
Okay, if you want, Lasso is of the order of seconds. This is of the order not of minutes, but some hours. So it's very slow up to now.
Okay.
But we would like to speed it up. Thank you.
Great, thanks.
So in your greedy ranking, I saw that for FNN, it deselects the parameter which is speed. So don't you think, I mean, like if you try to make sense physically of the parameter selection here, speed is one of the most important, I thought, is one of the most important parameters for deciding the geoeffectiveness of any interplanetary structure, because it actually it governs the first, ram pressure that is, that the magnetosphere of the Earth is subjected to. So how do you make sense of that parameter selection?
You mean of the velocity?
Yes. For FNN, I guess.
Okay.
Yes.
For the feed-forward neural network?
Yes.
Okay, physically, maybe this is out of my expertise, but I guess that at least physicians to which we told, they told me that the most important feature for the magnetic field, at least, is the zeta component, because the CME goes in that direction. Okay, so currently we took the third component. And they also told me that the X component of the velocity should be relevant. So I guess that it has a physical meaning. Again, it is not so, it is never in the upper ranking, okay? And I guess that it's because of this, because we are not only taking into account CMEs, but also high-speed trim and other geoeffective events. I hope I replied, okay? Okay.
So that concludes session 4 on the sun-space weather connection. Now we are moving to session 5, that is novel techniques for data analysis, machine learning, and deep learning. And the first talk is remote by Anna Maria Massoni from the University of Genova, Italy. She's going to talk about machine learning techniques for solar physics and space weather. Anna.
Okay. I share my screen. Okay, can you see? Can you see my screen?
You can see the screen, yeah.
Okay. Okay, so first of all, I would like to apologize because I was supposed to be in person in Cape Town, but at the end I couldn't fit this travel, so sorry for that. Well, my talk the use of machine learning technique for solar physics and space weather. And in particular, I will talk about 2 different applications. One deals with flare forecasting and the other one with the prediction of coronal mass ejections arrival time. These 2 applications are related to 2 projects I'm involved. The first project is a European project. The title is ARCAF, Active Region Classification and Flare Forecasting, and is a project that led by an Irish institution, the Dublin Institute for Advanced Studies. The second project is A-Extreme, is funded by an Italian foundation, the Fondazione Compagnia di San Paolo, and deals with physics-based AI for predicting extreme weather and space weather events. Let's start with the application concerned with the first project, so ARCAF. The application deals with flare forecasting. A lot of people are working on this project. In Genova, Edoardo Legnaro, Sabrina Guastavino, with in strict connection with people from the DIAS. Shane Maloney, that is the PI of the project, and Paul Wright overall. All of you know that if you have a flare, this flare comes from an active region, but is not true the vice versa. So not all the active regions will originate a flare. So if you want to solve the flare forecasting problem, you have to understand which are the characteristics of the active region that will produce a flare. So first of all, you have to localize the active region. You have to extract from the active region some feature characteristic of the active region. You have to pose a question, for example, if in the next 24 hours we will have a solar flare of a specific class, for example, class C or M or X, then you have an answer, yes or not, and if your prediction, for example, yes, is corrected and you have a flare, you are more than happy. But in this chain, the most important thing is how you extract a feature from your image. And you can follow 2 different approaches. In the first one, that is the more traditional, if you want, approach, you have some images of the sun. For example, you have images from magnetograms, and you perform feature extraction by using some pattern recognition technique. Then these features are related to the morphology of the active region or to the physics, to, for example, measure of the magnetic fields and so on. So you can feed a traditional neural network, like a fully connected neural network, with these numbers, and at the end you have your answer. A more modern approach is the one to use deep learning. So you don't touch your input image and just you put your image as input to a convolutional neural network. Some convolutional layer reduce the size of the image, and at the end you have a vector where in this vector you just have the more important information from your original image. You feed, again, a fully connected neural network with this number, and you have your answer. The first approach is a machine learning approach. The second one is a deep learning approach, and both have pros and cons. The approach we follow in the ARCAV project is the second one. So we want to use deep learning models to solve the problem of flare forecasting. The ARCAV project has 5 different objectives. 2 of them are already reached. The first objective is to perform classification of the active region by using magnetogram cutouts. The second one is the one to localize and classify the active region by using full disk magnetograms. Then the third objective is strictly related to the second one, because you have to localize, classify the active region and associate a probability of flare occurrence. And then we have the 2 last objectives that are the most ambitious one. For objective 4, we can use not just one image at a time, but we can use multimodal observation, full disk multimodal observations. And then for objective 5, we want also to take into account of time, and we want to use a time series of full disk multimodal observations. I show you now some results of, related to the first 2 objectives. Our Irish colleague prepared for us a data set consisting of about 60,000 cutouts extracted from SOHO MDI and SDO HMI magnetograms in the time range from 1996 up to 2022. For example, if you look at the image in the left part of the slide, they were able to extract from a single image a number of cutouts without active region inside, but just representing the quiet sun, and some other cutouts labeled, annotated with the class of the active region inside. As you can see, it is a very unbalanced data set, because we have 60% of cutouts representing quiet sun, and then alpha, beta, beta gamma delta, and beta delta classes according to the magnetic classification. Very, very unbalanced data set. We try to solve the classification problem in different way. The first one is a 6-class classification problem, so multi-class classification problem. We try to recognize all these different classes. Then we try to solve a 4 classification problem by aggregating the classes, the 3 last classes that are very, very few instances, and also as a binary class, quiet sun versus active region. Of course, this last problem, this binary problem, is very easy. We obtain a very high skill score. I show some results concerning the more complicated task to classify all the 6 different classes. As deep learning models, we studied and implemented very different approaches. They are listed in the left part of the slide. We use AlexNet, we use some transformer approach, and we also implemented our custom convolutional neural network. I show results just for the 4 models that are highlighted in the list. And for these models, we try to evaluate the performance according to the accuracy metric that measure the proportion of correctly classified instances with respect to the total number of objects in the data set. And we obtain rather high number, about 0.9. But if you look at the number in the first column of the table that represents the number of parameters that have to be optimized in each one of these 4 models, you can see that we can go from a high but not so high number, 2 million of parameters, up to 90 million of parameters for the vision transformer model. That is the one who gave us the best results. Just for this last model, I also show the confusion matrix, and as expected, the 3 last classes are the most difficult to classify. Then we go to the second objective, so the one of localize and classify the active region from full disk magnetogram. Our Irish colleague for this second objective prepared for us a second data set consisting of 3,000 full disk images. This time we just considered images from SDO-HMI covering the time period from 2010 up to 2022. And in each one of these images, they annotated the presence of active region. So they gave us the bounding boxes of these, the boxes surrounding the active region, together with the label of the active region. For example, in this case, we have 2 alpha active region and 1 beta active region. Well, on the right part of the slide, you can see some characteristic of this data set. Again, is unbalanced. The boxes that gave us have a very different size, as you can see in the upper right part of the slide. In the bottom part, you have the position of the centers of these boxes, and of course they are uniformly distributed with respect to the x coordinate, while this is not true for the y coordinate. And the last plot on the right bottom part is the height versus the width of the boxes, and so we can see that the majority of the boxes is very, very small. For this second problem, we considered again a lot of different deep learning models, and then we fix our attention on the one that is called YOLO, you only look once, in particular the 8th version of the model, YOLO V8. The architecture of this model is rather complex, as you can see in the right part of the slide. And it is available in 5 different versions according to the number of parameters to be optimized. The most simplest one is the nano version with 3 million parameters to be optimized, up to the extra large version that has about 60 million parameters to be optimized. For an example of localization and classification, if the result of the image that I have shown before is on the right part of the slide, the model correctly identified the presence of 3 active regions in the image. The model gave us the boxes that correctly surrounded the active region. Also, the label assigned is correct, 2 alpha and 1 beta, And the models also give us the probability that the labeling is correct. So in this case, we have high probability, 94%, to have 2 alpha active region and 92% of having a beta active region. To evaluate the performances of the model, we considered a lot of different metrics, specifics for the task of detecting objects in images. I do not want into the detail of the meaning of these metrics. In this slide, we have 2 metrics that are called MAP 50 and MAP 5095. The different behavior you see in the slides are the value of the metrics for the 5 different versions of YOLO as a function of the iteration in which the model is trained. As you can see in the left, there is no big difference with respect to the complexity of the model, while for the metric on the right, there is some difference, and the best one, the models that give us the best result, is the most complex one, the YOLO V8X large. Well, just some words about the 2 more ambitious objectives of the project: the use of multimodal images of the sun. We are planning to use EUV images from IAA, and from a deep learning point of view, we are planning to use bidimensional convolutional neural network with multi-channel images. And the last objective, by introducing the time variable, we will use a 3-dimensional convolutional neural network. Let's skip now to the second problem I would like to talk about, the prediction of the CME's arrival time. This is an application related to the second project, the project iExtreme, in which many people are working: Sabrina Gualtavino, Mattia Rossi in Genova, then Emma Perracchione in Torino. Emma has already gave her talk, and then some people from the Astrophysical Observatory in Turin, Dariene Terloni and Roberto Sosino, but many other people are working on this project. This afternoon, early this afternoon, there will be another talk related to this project, and the speaker will be Mattia Rossi. Okay, if you want to predict the arrival time of the CME, you can follow 2 approaches. One is completely model-driven approaches, if you know the magnetohydrodynamics equation, and the other one is a data-driven approach, and if you just use machine learning or deep learning applied to data at your disposal. Within this project, we try to combine these 2 approaches in order to have a physics-driven machine learning approach. And to do that, we consider the drag-based model. In the slide, you have the equation that is a different equation, describing the drag-based model in its simplest form, where we have CME acceleration, CME speed, and the speed of the solar wind. In the model, there is also the drag parameter, gamma, that is function of some parameter characterizing the CME and the solar wind, like the solar wind density, the CME mass, and the CME impact area. But this drag parameter depends also from a drag coefficient C that is unknown, and this is a big problem for us. Well, by the way, in the Mattia talks this afternoon, he will present an updated version of the drag-based model equation. Okay, if we know some initial condition like the initial CME speed or the age of the eruption, our problem becomes a Cauchy problem, and we can solve analytically the equation. And this is the solution of the equation related to the drag-based model. And this equation can be used to estimate the travel time, because the travel time is the value of t for which r is equal to 1 AU. Of course, if you use this equation, you need to have some accurate estimate of the parameters in the game, and you can have a measurement characterizing the CME from chronographic instrument, and you can also have a measurement of parameter characterizing the solar wind by some in situ instrument. But again, you do not have measurement for the drag coefficient. So our idea is to include the drag-based model into the loss function. First of all, we simplify the equation by performing some approximation to get rid of the sign function inside the equation. So this is the approximated version of the solution of the drag-based model. And we introduce a loss function made in this way, made of two terms. The first term, this one, is a data-driven term, like the second one is a physics-driven terms. In the first part of the loss function, in the first term, we ask the predicted time as a function of the weights of the network and as a function of the input of the network, and the input of the network are the estimated parameters, to be similar to the as a measured time of arrival as much as possible. In the second term of the loss function, we ask to have R as much as similar to 1 as possible. So two terms, the first one is the data-driven term, the second one is the physics-driven term. There is a parameter that is called regularization parameter lambda that balances the importance of the two terms. In particular, with lambda equal to 1, just the first term is considered, and so we have a fully data-driven approach. While lambda is 0, just the second part of the loss survives, and so we have a completely physics-driven term. We choose lambda equal to 0.5 in order to have an hybrid approach with both terms are equally balanced. Now, how can we estimate C, the drag coefficient? That is a very important point. We try to estimate C by using a neural network. So we solve in our big problem to estimate the arrival time of the CME as a cascade of neural networks. In the first step, we use a neural network that uses in input all the estimated parameters to estimate the drag coefficient. And to train this first network, we just use the physics term of the loss function. We look for the drag coefficient value that minimizes this function, and so that makes R equal to 1 given the observed measurement for the CME parameters and solar wind. Once the C coefficient is estimated, we consider a second neural network in which this value is added as input together with the other ones. And now, by using the full loss function made of two terms, data-driven and physics-driven, with this second neural network, we try to estimate the time of arrival of the CME. Okay, this is just a summary of these two steps. We can skip. We validate the method by using a data set made of 123 events. These are the source of the data. And we perform a statistical assessment by realizing 100 random realization of training, validation, and test set. And this is what we obtain. If you look at the error given by just the data-driven approach on a test set, don't look at the training and validation. On a test set, we have a 12-hour error in the prediction. But if we use our balanced loss function and so this physics-informed approach, the error in the prediction decreases about 2 hours. We have now 9.6. Again, as a last things, we can perform a feature selection in order to understand which are the most important features that impact on the prediction by using one of the methods cited by Emma before. And what we have seen is that there are 3 features that most impact the prediction. And they are the CME initial speed, the wind speed, and unfortunately the drag coefficient. So an estimate of the drag coefficient is crucial if we want to have a reliable prediction on the arrival time of the CME. Well, I'm done. I thank you for your attention. In this slide, there is the link of our research group in Genova. And just for your information, we have just now an open position to work at topics related to the iExtreme project. The deadline for application is September 4. So if you know someone that is interested in applying, you are more than welcome to pass this information. So thank you. Thank you very much.
Thank you so much, Anna. Any questions for Anna? So, Anna, I have a question to you. It can be also for...
Yes.
So, machine learning and artificial intelligence are the way for the future. And if you look at other fields, they are way, way more advanced than us in science, space physics. So, oftentimes we are looking for these scores, high scores of success. But, and we are looking for lots of correlations, but correlation oftentimes doesn't mean causality. So it's, we have to be careful with it. Are there any other indices that gives us a measure of false predictions? Also that you might actually have some high score, but that's actually another index or indices that tells you, yeah, you have to be careful. This actually might be a false prediction.
Yes, of course. Yes, of course. I just showed some score, the accuracy, for example, if I go here. Okay, for example, for this problem, I just use the accuracy that is a kind of overall measure, especially in a multi-class classification problem like this one. But we have considered a branch of about 10 or 15 different measures. that take into account of specific problems that you can have, for example, in correctly classifying the class that are less representative. Yes, we have a lot of different scores that can give you information on the overall behavior of the model or specific behavior of the model. Yes, we have this kind of, for example, just in the first, looking at the first classification problem, the one of classify the cutouts, we have seen that there was, looking at our different scores, so we have seen that there was something not clear. And we gave feedback to the Irish people working in the project, and we discovered problems in the data set. And so the data set has been recomputed. So the score can tell you that if there is something that is not expected or good enough.
So much. Any other questions? Okay, thank you so much, Anna.
Thank you.
Thank you. Let's move on to the last talk of, it's not the session will continue after lunch. Thank you. So the talk is by Robert Jarolim from the High Altitude Observatory in Boulder, Colorado, and he's going to talk about sun neutral radiance fields from images to 3D reconstruction of the solar atmosphere. Robert.
Yeah, thank you for the introduction. Can you hear me well? Okay. Yeah, this symposium is probably the best opportunity to present this multi-point view of the sun. This is exactly what we are using to obtain a 3D image of the whole sun. So this presentation is about how can we go from images to a complete 3D reconstruction of the solar atmosphere in EUV. So let me start with a brief motivation for this. But if you have seen the talk by Sarah Gibson in the morning, there's probably nothing to add here, but let me try to quickly state the problem that we have. When we view the sun, we basically view it two-dimensional as an image. In addition, it's line of sight integrated emission from an optically thin plasma, which makes it extremely difficult to interpret the structures that we actually see. So in order to better understand the dynamics of the sun and the structure of the solar atmosphere, it is important to have a full, complete 3D image where we can actually spatially localize structures. On the other hand, understanding better the dynamics in 3D also helps to predict space weather impacts. And also beyond the space sun-Earth line, we can use a 3D image to better understand the solar impacts on other planets in our solar system. Ultimately, we observe the sun only from the ecliptic plane so far, or like mostly from the ecliptic plane, but we observe other stars from various inclination angles. So in order to connect the sun to other stars, it is important to have a 3D image where we can also view the sun from different inclination angles. So this was the picture that we had from 2010 to 2014, where we had 3 parallel viewpoints with the stereo twin satellites and the SDO satellite. So this is a very limited number of viewpoints that we have available. So for this study here, we are trying to utilize those observations to combine them into a 3D image. So when we have this limited number of viewpoints and we want to complete our image of the sun, there's of course the opportunity to just launch new satellites. So this is what we are working on right now. But till we are at this point, it is important to use the existing observing capabilities to better understand the solar atmosphere. So what we propose here instead is to build, based on the existing observing capabilities, basically virtual instruments to view the sun from any direction. We can then use this approach for virtual instruments basically to place them in various inclination angles, like at the ecliptic plane, but also at non-ecliptic planes. The way that we do this here is with a method that we call sun neural radiance fields, or sun-nerves. The way it works is we use multi-viewpoint data from the existing satellite missions and combine this data into a 3D representation plus its temporal evolution into like a coherent picture. we can then use this reconstruction to render novel viewpoints from any direction. This method is based on a method which is called neural radiance fields, which is a deep learning method which uses a ray tracing approach. So this is very similar to a tomography method in that sense. The method works in a way that we have individual images from different viewpoints. Since we have the known locations of the observations, we can use those images and cast rays through the individual pixels. Our goal here is to reconstruct basically this volume. So the goal here is to reconstruct the volume of the sun. So this is our simulation volume, where we want to obtain basically the 3D reconstruction based on those images. So we cast rays through the individual pixels into our simulation volume, and along the ray, we extract individual points in terms of the coordinates points, X, Y, C, and T, which we then pass through our neural network. We model this here in terms of emission and absorption values. So per point, we get the emission and absorption coefficients, from which we then construct the emission and absorption profiles. Using then radiative transfer, we can obtain the final observed pixel value by just basically integrating both the emission and absorption profiles together. Since we have the known value from the observation, we can then compare our rendered pixel value basically to the observation and optimize the weights of our neural network to give us the right emission absorption values to predict the same value in the end. So for a single image, this would be very simple to construct, but what we are doing instead here is we do this for all the observations that we have simultaneously and also for all the pixels that we have in this image. So we're essentially probing this volume from multiple different points, casting points from different angles into this volume and reconstructing the observations based on that. So it is important here to note that this is purely driven by the data. So we are not building here a generative approach where we can arbitrarily sample like images. So it's not meant to produce realistic looking images. It's just based on the data that we have. And this also means that when we apply this to a new data sample, this requires a retraining from scratch. So the first step that we did with this is to validate that this method actually works correctly. And we did this with a synthetic data set where we actually have this full 4π information. So this is done with this MHD simulation from Predictive Science, where you can see on the right-hand side here, the images that are rendered in EUV. So this is, those are snippets basically from the data set that we are using. And specifically, we tried to mimic basically our observing capabilities, where we only used ecliptic viewpoints, which are shown here in magenta, as input for our fitting. So in the end, so the model training is only performed with the ecliptic viewpoints, and in the end, we compare to the other viewpoints which are out of the ecliptic plane. So that's strictly separated in this case. So here you can see the results that we obtained from this first application. At the top, you can see basically the samples from the data set. So only the with increasing latitude. So from left to right, we increase basically the latitude of the observations from ecliptic plane to the polar view, basically. And it's important to note that basically only the frame on the left-hand side is part of the fitting of the training process. So the frames on the right-hand side are then used for the testing of the method. In the second row, you can see what we obtained with our sun nerve reconstruction. So the first frame, of course, matches because this is what is used for the fitting process. But then we can render basically new viewpoints at higher latitudes. And we can see that this is almost identical with what we have in our test set. But the network has no access to these observations at the time of training. So only by comparing those pixel by pixel, we can actually identify the regions of stronger errors. And we can see that this mostly ranges in the range of like 2% error here. In addition, we provide also uncertainty estimates, which we do by performing an ensemble run of the model. So this basically gives us regions where it's increased model uncertainty. And we can see that this primarily increases at regions where we have higher complexity, like the active regions, or closer to the limb. And when we compare this actually to the comparison with the ground truth, where we have this difference, we can see that this is in quite good agreement. So we can use this uncertainty estimate in the end also to quantify with the actual observations how far they are off from what we expect, or to estimate errors in our reconstructions from the observations. With this, we can basically move forwards to observations. But the first thing that we have to appreciate here is the difference between the individual instruments. So we are dealing here with observations from SDO AIA and stereo A and B EUVI. So we use 4 channels of the EUV observing instruments. And what we need to do first here is to intercalibrate the data sets. So here we built on a deep learning method, which is called instrument-to-instrument translation, which first is applied to homogenize the data set. From this, we obtain then 3 viewpoints of a homogeneous data series from the 3 satellites, basically, which we then try to reconstruct into a continuous 3D image of the sun. So here we use specifically like an ideal angle from 2012, where we have a good separation angle between the 3 satellites, and we use 14 days of total observations in time to obtain this reconstruction of the sun. And here you can see the results that we obtain from this. We can use a static point in time and render viewpoints in the ecliptic plane, but also out of the ecliptic plane, basically flying over the solar poles. And we can also model the sun here over time. So in the end of this video here, you can see also when we pan up, we further evolve time. And you can see that we also capture a solar eruption during this time frame, which basically allows us here to view this solar event from like a polar angle even. So this essentially gives us like a first look, so to say, of the solar south pole. It's an approximation, of course. But just to see where this comes from, basically all the arrows that are indicated here correspond to the individual observations that go into this reconstruction. So essentially we have a full 3D, a full scan of the sun over time. And in the center here, you can basically see the reconstruction of the south pole. Most prominent here is this polar coronal hole. And when we compare this to the actual observations, we can see that we have that we observe it partially. But for example, for SDO, it's obscured by outshining effects close to the poles. But from our reconstruction, we obtain this consistent image of the solar southern polar coronal hole. And we can also apply this method not only to the single wavelength channel, but we can also apply this to the other 3 wavelength channels. So since we have these uncertainty estimates, we can use them actually to estimate potential errors here. And what you can see basically is, again, this increase in latitude until we reach the polar view here on the right-hand side. And when we look at the uncertainty estimates, we can see that we have more increased uncertainties close to the boundary. But throughout, we construct basically with a high certainty this coronal hole feature. Since we have this 3D information, we can actually make use out of this by extracting slices from it. So we have this full 3D image, so we can actually extract this 3D information. So what you can see on the left-hand side here is an observation from stereo, where we have this slice here of interest in red. And then we can use our 3D representation to render the side view. So this is the view rendered by SunNerve here, where the limb now, where this slice here aligns now with the limb. And then we can extract the slice above this limb, which is shown here. So here we can see a couple of prominent features. We have this active region up here. We have a coronal hole down here. And then we have also this filament channel down here. So when we compare this to our slice of emission, we can see that we have here this bright active region, which is well rooted in the solar photosphere. We can see also this this intensity decrease from the coronal hole, which also goes all the way down to the photosphere, basically, or to the lower corona. And then we can see also here this solar filament, which appears as a dark cavity elevated in the solar atmosphere. We can also use this as a time-dependent model, where we apply this to this filament eruption here, and we can extract from this additional information in terms of the height from the solar center. So you can see here how the filament slowly starts to rise and then quickly erupts when the video plays again. And you can also see in the integrated emission the dense plasma that is being ejected outwards. So from this, we can actually extract slices. And from this, you can see basically over the individual time steps, you can see how this plasma is being ejected outwards. And most interestingly here, so at the top is the emission profile, at the bottom, the absorption of this event. with the slice indicated here on the left-hand side. And here you can also see how the flare loops are formed after this eruption. So with this, I want to give you a quick summary. We use basically multi-viewpoint satellite data based on our existing observing capabilities to obtain a 3D reconstruction plus its temporal evolution of the solar atmosphere, from which we can then render novel perspectives. We can also use this to extract basically 3D information and use this to view solar eruptions in terms of their 3D evolution. And most importantly here, this approach is directly relevant for future constellation missions, where we can better examine how many satellites we can use for those reconstructions and what the impact of the individual positions could be on the final reconstructions. But also this method can make direct use of future constellation missions to incorporate them. So at the moment, we're actually also working on incorporating Solar Orbiter into those 3D reconstructions to have like a uniform picture of the sun based on this multi-viewpoint data. So the paper is already published. You can find it here. We're also working on an extension for coronal mass ejections, for reconstructions of coronal mass ejections. And this year we are extending this approach with emission and absorption values to more physical quantities where we model the density and temperature. I finally leave you here with this virtual fly through the solar system. Thank you for listening.
This is very neat work, and I was kind of thinking that this is a nice complement to surface flux transport models, which take the photospheric field from observations close to the ecliptic and then evolve it to get the polar fields. So one could also apply reconstructions of the coronal field on those SFT models and then compare it to what you were doing. Is this something that has been thought about? Are you thinking along those lines? Or are you open to this?
Yeah, I mean, like any comparison is useful. I think at the moment we are primarily considering like other EOV observations as a comparison. Also, I mean, like definitely considering the polar fields is of high relevance. Like this method really needs some spatial extent to make use of this. So I'm not sure how it can connect directly to magnetic field in that sense. So we are primarily limited to something that's more extended, like the corona.
We can talk later, maybe. It can be done.
Yeah. Okay. Sounds good.
Yeah, nice talk. I think you touched on my question at the end, that this is purely 3D reconstruction of the stereoscopic emitting plasma. So there's no physics in the model in terms of the magnetic structure or anything. Is that right?
That would be ideal in the end, yeah. So it's like something that we're working on. But it's a process. Of course, we're doing like step after step in this, but coupling this with the physical equations, with the magnetic model, and making this basically an MHD equation, like an MHD solver in the end, would be the ideal scenario. So definitely, yeah. I think for the next step, what we're doing is getting this to more physical quantities in terms of temperature and density estimates, and with this we can couple then to the magnetic field. So that's an ongoing process. Yeah. Thank you for the question.
Really fabulous movies. Where do I get them?
You will find some references in the paper, and we have them also on YouTube online, and there's some showcases.
Okay,
yeah.
Excellent. Thank you very much.
What's the minimum number of So what is the number of minimum viewpoints and locations that you will give you for broadcasting?
So the question was about the minimum number of viewpoints. The answer to this is, I mean, like we are working here with 3 viewpoints, and this works pretty well. We would further need to examine if this makes like a bigger difference, if we would have them like closer aligned, if we would get more reconstructions. I can comment more on this about for CMEs, for example. There we know that if we have at least 3 viewpoints, we get very good reconstructions. 2 viewpoints give us already proper directions, but not a full reconstruction. So for example, for the CMEs, it's much more prominent than for the EUV images. I was showing here this, like this eruption. Yeah, this actually is reconstructed from only 2 viewpoints. Ideally, we want more viewpoints, but this works in a way that we build on basically first like constructing with 3 viewpoints like the global sun, and then focusing down on a single event with 2 viewpoints. So we already have a good approximation, and we just try to pin down with the remaining 2 viewpoints on this exact location. So this is based on like having first an estimate about the geometry and then further pinning it down. But like I think the way forward is definitely adding more viewpoints and to see how this further improves actually like in the detail what we reconstruct from this.
Let's thank over again.
Yep.
So this concludes the first part of the session 5. But before we leave, I think Marco, probably you have some announcement, but okay, you don't have any announcement. That's good. Yeah, I'll give you, yeah, go ahead, Piantier.
So on behalf of the Astronomical Society of India, today we are celebrating India Day. We have a booth. India has been making major progress in space science missions as well as ground-based observatories. We would love our solar physics friends to stop over. 3 p.m. at the India booth downstairs. We have some games, some giveaways, and you could see people like Dipankar in traditional Indian dress. Stand up, Dipankar. So you're going to see more of us like that today. So you all free food. Yeah, that the conference organizers are going to give you free food anyway. So you're all welcome. I look forward to seeing all of you there at 3 p.m.
Okay. Yeah. So before we break, yeah, thank you. So I know this is not the end of Symposium 390, but I want us really to give a hand to Marco and the organizing committee for, it's really a headache to organize such a symposium, but they really deserve it. Thank you so much.
Good afternoon, everybody. Welcome back. So we will start this session after lunch by continuing the previous session on novel techniques for data analysis. So we have two more contributed talks. And then we will start at 2 o'clock. We will start session 6 on lessons learned and future developments with an invited talk and then 2 more contributed ones. So we start with Spiros Kassapis, who will talk about examining the ability of machine learning models to predict SEP events, utilizing 2 solar cycles of observations.
And yeah, awesome. Well, thanks all for being here. We're skipping lunch to listen to me. So yeah, my name is Spiros Kassapis. I'm a postdoc at NASA Ames Research Center. And today I'm going to be talking about examining the ability of machine learning models in predicting SEP events utilizing 2 solar cycles of observations. And in previous, I guess everyone here knows what SEPs are and how they can potentially harm like Earth. So I'm going to skim through these. Our community has tried to like predict SEP events using physics-based models, empirical models, probabilistic models, and machine learning-based models. So what you're going to hear today from me is the last part, machine learning. So without further ado, this is an extension of a previous study that we published in 2022. Okay, great. So yes, in our previous study, we showed that using machine learning and the SMART dataset, so the space weather MDI active region patches, we can correctly predict whether a solar flare will lead to a SEP event 72% of the times in a experimental setting, and I'm going to explain why. The SMART dataset provides a leading time of like about an hour for forecasting SEP events. And one of the biggest limitations of that study was that only 65 positive events were included in the dataset because only 65 events were the ones that happened during like SDO's lifetime by then. So the goal of this study is to like do essentially the same thing we did in that previous study, but augment our dataset, including an additional source cycle. And we wouldn't be able to do that without this work by our colleague, Kosovich et al., who created the SHARP SMART dataset. So Kosovich et al. Combined the SMART, so like MDI data, and the SHARP HMI data datasets into a single product for enhanced space weather forecasting. He filtered, he rescaled, and he merged parameters, creating a uniform multivariate time series from April 4, 1996, so the beginning of SOHO, to December 13th, 2022, when we started working on this. And Kosovich et al. Keeps updating these datasets, so please scan the QR code. It's a pretty interesting study. Paul also identified time-like relationships between magnetic field properties of active regions and solar flare indices, suggesting some predicting potential of this data set. And therefore, that's where I come in. I took this data set in order to predict SCP events. In my work, I use 5 keywords, so 5 physical parameters included in this data set, this published data set, is the total line of sight unsigned flux, is the unsigned flux R near polarity inversion lines, is the mean value of line of sight field gradient, the vertical component of the total unsigned flux, and the mean value of the vertical field gradient. And the data set, amongst other parameters, also includes spatial parameters like the current on latitude and longitude, as observed for every each of the active regions, including the data set. So in my study, I'm not going to be using the coordinates themselves, but I'm going to be calculating the angular distance between the active region and the Earth's magnetic foot point using these 2 parameters and this equation right here. So 6 different parameters that I'm using. How we created the data set. There is 2 types of active regions that we study here. There's what we call quiet active regions. They're not quiet. They produce flares, but they do not produce SCPs, which is our goal in this study. And then we have SCP producing active regions. So active regions that produce flares that later produced solar energetic particle events. Then for each one of these active regions that we have in our data set, we use the SMART Sharp dataset timelines provided by Kosovitz et al. Then using the NOAA flare data, we connect essentially the SMART Sharp datasets with the flare times in a way that I'm going to show on the next slide. And we also do a flare SCP coupling. This study does SCP prediction based on flares. Therefore, we have 2 types of flares. We have SCP producing flares, which we note here as positive. And we also have non-SCP producing flares, so flares that did not lead to an SCP, which in this study I'm going to be noting as negative. How did we pick our data from the SMART data series? Here, this is like a typical, this is how like a timeline in the Kosovitz data set looks like. This is for active region 10.18.0 for unsigned flux and for the R value. And in the gray dotted lines, you're going to see the beginning time of each one of the flares that occurred within this active region. Not all of them. The gray ones are the ones that did not produce, they did not lead to an SCP. But in green, you're going to see the one that did produce an SCP. And in red, you're going to see the starting time of the SCP and the flare occurring, the flare starting time right before the SCP. In this study, oh, that's weird. Why? Okay, so in this study, we do like these should be 2, 5, and 10 hours worth of prediction. So we pick the SHARP or SMART data point that is like 2, 5, or 10 hours before the starting time of the flare that either produced an SCP or did not in order to do prediction. And so the final count of the flares that will be used for SCP prediction in this study is like 110 positives and 3,246 negatives. So you're going to see that this is a problem that the community has discussed a lot. There is like a very big imbalance in the data set, which I'm going to discuss later. Oh, colors are not here either. Weird. All right, so we have in green, well, thankfully the colors are here on the on the plots. In green, you're gonna see the positive events, so the histogram, the density histogram of the positive events, and in red, you're gonna see the density histogram of the negative events. What I'm trying to demonstrate here is that for the 6 values, so this 6 keywords that I'm training machine learning methods with, there is like quite high overlap within all keywords. So this kind of hints us that this is a very difficult problem for a machine learning method to deal with. But there is a couple of keywords like the unsigned flux and the angular distance to the magnetic foot point that have some distinctive capabilities. And this is going to be even more clear when we calculate the Anderson and the Darling statistics. So you're going to see that for the unsigned flux and the angular distance, the Anderson and the Kolmogorov are quite higher, which kind of tells us that there is some distinctive capability between like SCP producing and non-SCP producing flares within these two data sets, the positive and the negative. And I'm going to discuss later what regular and clean is, but this applies for like all different data sets that we used in this study. Next. Okay, so yeah, the dataset variations. We deal with like many different problems, just like we go from like operational to experimental. We have two types of different datasets that we study here. It's something pretty common in the community. So in the first hand, we use regular and clean. So by cleaning the dataset, we omit the flares that did not produce an SCP in an SCP producing flare active region. So in this way, the problem gets reduced from flare-centric to AR-centric. We essentially predict whether an AR will produce an SCP rather than a flare will produce an SCP. And then what pretty much every study does in this, like in SCP prediction, the balanced and imbalanced case. So we have like a vast imbalance between positive and negative. So we have, in this case, an imbalance ratio of 1 to 30. So two types of training and validation SIMs are used in our analysis. One where the positive and negative data sets are balanced, and one where the 1 to 30 imbalance is retained. So you're going to see here that obviously when we use the regular data sets, so no cleaning happening, and the imbalance, so like this kind of simulates an operational setting, which is the most important in this case. And when we use one or the other, it's like semi-operational. And when we use the balanced and clean data set, we deem it as experimental. And our results. So we trained two types of machine learning methods. We trained support vector machines and regression models. We train support vector machines. We use 4 different filters to test capabilities for all 4. And the same we do for regression models, 2 different regression models. What is interesting here is that, great. As I hinted before, and as we saw at the histograms that unfortunately do not have colors, the unsigned flux, when using the unsigned flux, the R value, and the angular distance, we get the best results for pretty much all the machine learning methods that have been tested. We go up to like 0.66 for the accuracy. And here we compare our results with the trained models of our previous study, the Cassaps et al. 2022. So we use 5 different metrics to evaluate our model's performance, which is the accuracy, the TSS, the HSS, the false alarm, and the F1, just to like get multiple views of like what our results look like. And what is interesting here in this study is that although in the experimental setting we don't see any increase in our results, merely like let's say a decrease within like the margin of error, by increasing twofold the number of data, we get an increase in the operational case. So by increasing the number of data, we do get an increased predictability for our operational case, but still in the very low, like 60s, even like 50s of accuracy. What's interesting is that also our false alarm rate has increased by a lot, which kind of signifies that there is going to be like more false alarms than the previous study. But yet again, for all the TSS, HSS, and I'm sorry, for the F1 score, we get better. We get a decrease in the false alarm rate, so we get less false alarms. So compared to like our previous study, these results do make sense. There is some predictive capability, but still, we are not there yet. We also compared with Lavasa et al. With her flare noisy. So this is a study that had like a similar setting. It's kind of tough to compare between studies because different data sets are used, etc. But this study had kind of like the similar setting with our. So we compared with their flare noisy linear SVM model with an imbalanced data setting, and their prediction indicated generally better performance as it exhibited a better TSS and HSS score. But the good thing about our current model is that our current models is that they demonstrated a significantly lower false alarm rate than what was reported by Lavasa et al., suggesting that it's less prone to incorrectly predicting SCP events. So just to jump into the conclusions, we utilized 2 solar cycles worth of data from SOHO and from SDO to train machine learning models to predict SCP events. Our statistical analysis shows that the vertical component of the total unsigned magnetic flux, the unsigned magnetic flux are near polarity inversion lines, and the angular distance between the active region and the Earth's magnetic food point are the parameters that are related the most to the SCP prediction problem. So these are the parameters that we hope that the community is going to be using in the future. When trained and tested in an operational setting, SVM and regression models perform better in the presence of more data. So 2 source cycles instead of 1 from the previous study. And although in an experimental setting, the models accuracy can reach up to 0.7. In an operational setting, the accuracy decreases down to 0.56, showing that the low-dimensional SMART-sharp dataset can predict reliably in SCP. And the last and most important point before I close is that this study really showed that future improvements in the problem of predicting SCP events using machine learning should use high-dimensional data, deeper machine learning models that can better capture the underlying dynamics of SCP production. We can use methods like the one that Dr. Emma discussed, but we're not going to get anywhere close to like having reliable operational prediction if we keep using low-dimensional data in the expense of, like, let's say, time. That's it. Thank you very much for your attention. These are the 3 papers that we've published in this topic. Yeah, thank you so much.
We have time for a quick question. Yeah, can you use one of the microphones, please?
So SAPs are biased towards the west limb, right? What you use in a magnetogram, you know, you use disk observations, right? So I wonder if you're creating a biased data set because active regions that you study may produce SCPs, you just don't observe them from Earth, right? And so maybe for future, you may want to include observations on the disk from different vantage points, like solar orbiter, for example, then you can match better. But I wonder if some of your statistics is skewed because of that bias selection.
Yeah, absolutely. In this case, we only use like SDO or SOHO, so like just a single vantage point. I totally agree with what you're saying, and that talks to like my point that we should use like more augmented data and like deeper networks. Low dimensional data only for one instrument seems to be not enough for the problem or for having like a reliable operational prediction. Yeah. And just like a plug for those who are in the SCP area, like there's this workshop at Georgia State University that we are running, my colleagues are running. So if you're interested, please.
Thank you. Let's thank Spiros again. So our next speaker is Mattia Rossi, and he will talk about machine learning-based dynamics of interplanetary coronal mass ejections using deterministic models.
Hello, everyone. Okay, hello again. First off, thanks to the organizers for the opportunity to present this work today here at this stunning event. My name is Mattia Rossi. I'm a postdoctoral researcher at the Math Department of the University of Genoa. And my talk will be about a combination of deterministic model with a machine learning approach to study the dynamics of interplanetary coronal mass ejection, specifically the travel time. So this work has been going on jointly with Sabrina Guastavino, Michele Piana, and Anna Maria Massone, who has just delivered a talk earlier. And it is supported by within the same project AI Extreme that also Emma and Anna mentioned before. Okay, so as you know, CMEs are particularly relevant for space weather monitoring in the sense that they can be correlated to geomagnetic storms, which in turn significantly affect our nearest space infrastructures. So this can be translated into direct damages, for example, degradation of the materials involved, or most likely it can cause disturbances, for example, communication disruption. So in these regards, it becomes essential as a safety measure to try to estimate the CME's travel time as accurately as possible. And historically, the forecasting problem has been addressed in several ways. The first one, say, relies on empirical models, so basically linear fitting between the initial speed of the CME and the effective acceleration were performed, and using simple kinematic relationships such as the law of uniformly accelerated motion were used to compute the time at 1 astronomical unit. Later on, way more sophisticated and accurate models were conceived, such as the one based on magnetodynamic simulation, which have the advantage to be really accurate, but they can be mathematically challenging, especially from a computational viewpoint. They can be demanding in terms of the resources, for example. So out of this, as a trade-off, a family of models basically were proposed under the umbrella name of drag-based equations, where essentially the CME front is modeled as one-dimensional, moving in the radial direction. And this equation, probably you have seen that before in the second part of Anna's talk. And the main assumption is that essentially the CME moves under the effect of a quadratic drag, which is expressed by the right-hand side here, depending on the value of the ambient solar wind and the drag coefficient in front of here. Then in the era of machine learning and deep learning algorithms, purely data-driven models were used for the same goal. And the idea was to feed neural network with either data extracted from the observation of the CME, so geometric parameters, physical parameters, or directly the coronographic images, for example, from LASCO coronagraphs. And the typical mean absolute error in the prediction, according to the latest literature, is of the order of 11, 12 hours. So in our approach, we would like, as an update of what you saw this morning, we would like to combine, to physically inform the purely machine learning algorithm with the information coming, from the drag-based models to improve this number here. And the idea is to present two refinements of the standard drag-based model and try to use the simplest of these models here to design loss function in the spirit of what Anna explained earlier. And we will see a little update in the improvement of the number of the error of the hour of the time of travel. And as an ongoing work, we would like especially to include in this process the most refined version of this family of models that I'm going to discuss in a while. Okay, so the first one you've seen before, this is the standard drag-based model, which assumes that everything is constant in here. So during the propagation, gamma and W is fixed. The only problem that we have typically is the uncertain parameter C here in the expression of gamma, where rho, A, and M are the density of the wind, the impact area of the CME, and the mass of the CME. So we need to treat that with some care. But apart from that, there are other, let's say, limitations coming from the model. Specifically, we have that the value, the solution V equal to W is an equilibrium. So, and in particular, is an asymptotically stable equilibrium. So basically, is a sink for our model. So everything if you start with an initial velocity of the CME, you cannot overcome this barrier. So you are either monotonically accelerated or decelerated up to this value for infinite time. And this is not what typically happens when you treat real data. I mean, most of them behave like that, but there are some that are left out. And so we would like to see a better version of this model in order to include also this data or try to make it up for. The first way out is to consider a 2D extension of the standard drag-based model. Well, I don't have the time to explain all the details, but essentially now we lose the possibility to have an analytic solution because we consider variable value of W and gamma, where we use 2D maps pre-computed for the density and the width speed using Parker Solar solution. And we inject subsequently the time dependency by switching on basically the sun rotation in the integration of the equation of motion. So with this, you obtain basically a way more complicated model that in principle can overcome the problem of the speed condition that I mentioned before. Moreover, we used also model for the propagation of the impact area, namely either the so-called ice cream model, where essentially the CME front is modeled as a spherical cap on top of a cone, or a torus-like shell in the picture here, and it typically it is performed in the work by Ternation in 2011 in AP in Astrophysical Journal. It's called the graduated cylindrical model. Finally, the third model that we consider, and this is driven exactly by the theoretical argument that I was saying before, that we have this barrier with the wind, and it is what we have called the extended drag-based model, in the sense that we added this constant term here, which is an extra acceleration that could be either positive or negative. So you can assume it as also a deceleration that takes into account of all the complicated interaction that you can have with the surroundings, also with the background medium, that is not attributable to solely to the drag. And the advantage of that is that you can still have an analytical solution. So this can be used in combination with the machine learning approach. And you do the job, basically, this is exactly what you are looking for. You move the asymptotic equilibrium away from the value of W. So in principle, you can overcome now the value of the solar wind, and it is compatible with the dynamics depending on the value of the acceleration A. The solution, the analytical solution is case defined. Here is just one example. It depends on the value of A and on the value of the initial condition, but by standard calculus techniques, although it looks quite cumbersome, you can always find a solution of this type, both for V and for R. Okay, so this, as I was saying, was driven by a theoretical reasoning. So let's test this. And we consider as test case a quite seldom event, the solar orbiter and wind spacecraft alignment that happened in November 2021, while radially separated by a heliocentric distance of about 0.13 astronomical units. And the two spacecraft were invested by a CME. So as pointed out also by Regnault, this in a work of this year, there was an extra acceleration acting between the two magnetic clouds at Solo and wind locations. And we used our model essentially to compute this extra acceleration that can be measured essentially from the time series computed at the two spacecraft locations. And as you can see from the three curves in the middle panel here, we have a quite good match. These are curves that represent our acceleration, the acceleration plus the drag acceleration at Solo, and the acceleration plus the drag acceleration at wind. And this is also testified by the trend of the radial distance computed for example, in this case, at wind location, which independently of the value of the solar wind that you consider, so you can have either a slow or a fast solar wind, you obtain an error that does not exceed the 5% in terms of relative distance. So let's come now to let's incorporate the machine learning part. And the idea is to consider a procedure that Anna explained earlier that we do in our group. So essentially here consider the first model for simplicity, but you can consider even the third, we used as input parameter the values that we have seen so far, and we construct a first neural network to predict the value of C, so the drag coefficient, which was this uncertain parameter, by a purely data-driven, physics-driven loss function. And you can use either the radius or the speed. Then we move to our target, so to the time, to the prediction of the time travel, by combining both, let's say, data-driven and physics-driven loss function, either in the expression of R or V, using the solution coming from the drag-based model. And in this case, we can use either the first model or the third one. The important part here that I would like to stress in the construction, in the architecture of the neural network, is that we don't really need actually the value of C, especially for a new input coming for operational purposes. We would like to have immediately the value of the time at 1 astronomical unit. And this can be done because we design a neural network such that indeed the input coming from the first one is optional. If you want, you can include that, or you can just simply leave it out, so you can get rid of that. Of course, it improves the prediction, but it is not essential. So this is something that actually we would like to have. There are some caveats, as I was saying earlier, now in the use of these loss functions. Of course, you have to have a dynamic which is respected by the model. So we, for example, using the first model, we have the speed condition that I mentioned before. And actually, there is an extra one coming from the computation of C. So in total, you have to discard about 40% of the data. And the ways out of this is to use the second model, so the more realistic one, to generate synthetic data in order to compensate the undersizing. Or, and this is in progress, use the third model, the extended one, to include the events that were actually dropped in the first place. These are the numerical results using the first and the second model. So as you can see, we gain something of about a couple of hours with respect to the purely data-driven models. So we are about 9 and 10 hours in the mean absolute error basically computation. The test here is done in the left with synthetic and real data, and here just with real data. It doesn't change much. Of course, you have to suitably tune the ratio between synthetic and real data that you use in order to have basically a sensible prediction, so that you have that you don't overfit basically your network with just synthetic data. But in principle, the bottom line is that the synthetic data helps the prediction with some care, so within some trade-off. Okay, so I think I'm almost out of time, so I leave here the conclusion. Essentially, we have 3 drag-based models that we can use in combination with a machine learning approach to help the prediction of travel time, and we reduce this number of about a couple of hours. And in particular, the extended drag-based model seems to be seems to have the peculiarity to better describe the dynamics of a coronal mass ejections, and so it is a significant advance in predicting the travel time. But this we have, of course, to check, to verify in future work using the approach of the neural network that I've explained so far, using exactly this model here. So thank you. I'm done.
Thank you very much, Matti. Are there questions? No questions. Let's thank the speaker again. Thank you. So with this, we have concluded session 5, and we will now move to session 6 on lessons learned and future developments, and towards a 4-pi view of the sun. And so for that, we invite Noor Rawafi to do the first invited talk about the Firefly 4-pi constellation, going above and beyond in the heliosphere exploration.
Good afternoon, everybody. So this is what you see down there are the full report of the study we did for the decadal. There is also the white paper, and there is also another white paper led by the members of the international community. All this material is available for everyone to look at. By the way, our white paper was the most signed white papers submitted to the decade, and it was signed by, I think, over 350 people. And at a certain point, we have to stop that. Anyway, yeah. If you go to the websites of some of the big agencies like NASA, ESA, or the other agencies as well, you will find science questions like these ones, which are extremely challenging. These are big, big questions that necessitate a lot of thought, but also a lot of investment quite a bit of investment to answer them. And it basically goes around how we interact with our star and how to live in harmony with it. And to illustrate this, there is absolutely no better examples than the May 24 solar storm, which was fantastic. And I believe many of you have witnessed it. Where I was, it was totally cloudy. We didn't see anything, which is a pity. But anyway, there was many events in over a few days, and they drove the Earth atmosphere like a little bit crazy, which was good for us scientists, but also for other folks. They were not looking at it necessarily. Anyway, this is what we have to deal with going forward. And if you will, to summarize the whole thing, it has to do the connection between the sun and the Earth, but it actually goes way beyond the Earth. It's now that we are thinking to send a man back to the moon and land women for the first time on the moon. We have really to think a little bit beyond our protected environment here on the ground. Even further down the road, if we are thinking to go to Mars or other places, then the interaction with the sun takes another dimension. And there is no better example than this one. And I believe many of you would have guessed it. These are actually the 40 satellites from SpaceX that actually were diving and basically burning into the Earth atmosphere. And you see them one after the other, basically disintegrating into the Earth atmosphere. And that's space weather in real time, anyway. So why we are having issues to understand how the sun works and how to interact, how to deal with some of the phenomena that sends toward us. And the reason for this, there are some scientific challenges that are due to some knowledge gaps that we have. And these that are basically across the board. If we look at the solar interior, we have really a problem understanding the structure of the solar interior in terms of flows, but also in terms of how the magnetic field comes about, how the magnetic field is generated, where it is generated, and how it emerges to the solar surface to produce everything what we see on the solar corona and beyond. If we talk about the flows in the interior of the sun, obviously we are always constrained by this single viewpoint, and we don't really have a clear idea what is the structure of these flows in the solar interior. In terms of latitude, we don't know that we have a singular cells meridian circulation, or we have multiple cells. We also don't have any idea about the longitudinal variation. And even furthermore, you can extend that to the evolution through the solar cycle. We don't know if these flows change over the solar cycle. Another example of the gaps that we have to deal with is the polar gap. And from the ecliptic observations, obviously we cannot see the poles clearly. Solar orbiter will give us some hints, but we need definitely a better platforms to give us a clear view to the poles of the sun, which are necessary to understand the interior of the sun and by consequence the solar cycle. If we move to solar atmosphere, and here this is a beautiful movie from the Solar Dynamic Observatory. Obviously, we see all the dynamic nature of the sun and the solar corona in particular. And it goes without saying that if you don't follow any of these structures on time, you're actually losing knowledge. You are losing information. And that's probably one of the main limitations of observing the sun from a single viewpoint. And one prime example is actually this small active region here. It emerged And within 18 hours, it actually unleashed this X-class flare here. Obviously, we cannot really do much about it because the magnetic fields measurements here are totally unreliable because they are beyond this 60-degree circle from the disk center, so we cannot really do much with them because of projection effects. And by the way, this type of events are really well connected to us here on Earth. Then, as I said, we cannot do really much about them. We cannot even try to predict them. Moving a little bit further out into the corona and the heliosphere, most of our knowledge of the corona and further out the solar wind and the heliosphere is based on models like this one from the predictive science, where they are trying to predict the structure of the solar corona for a total solar eclipse. And they do really an excellent job. Overall, they reproduce the structure of the corona, but the details are missing. There are a lot of issues, in particular lower down here, that do not match the reality. And the reason for that is basically the boundary condition that these models are using. The magnetic field, first of all, we are using for the photosphere, which is not the ideal layer. Actually, a better boundary condition should be higher up in the chromosphere, but that's not reliably, that is not routinely available to us. So we have to use the photosphere. But these type of synoptic maps are built over whole solar rotation. So most of the magnetic fields you see here are totally outdated. The only magnetic fields that are fresh are around the central meridian, which is around here. Magnetic fields on this side here are about 27 days old. And we know how when you look at any magnetograms on the sun, we see the field is evolving like crazy. So by nature, these magnetic fields are wrong. But furthermore, look at the poles. The smearing we have on the polar region, that's another thing. So in a way, there is also another limitation that is a consequence of all this. We are basically simulating a dynamic system with steady state models. And that's why, because simply, and by the way, I have to make it clear, it's not really the fault of the models or the modelers. It's simply we do not have the data. It's as simple as that. And this is actually one great example. This is actually a picture from John Linker. You recognized him there. He was giving a talk at the EGU, I believe, last year or the year before, and they just took a picture of it, and I've been using for quite a bit. And he basically was saying, okay, to model the sun, you need basically time-dependent models, and he lists what we need for it. I think the first thing he says, we do not have data from all over the place around the sun. The sun is this 3D thing, but we are observing it from one viewpoint, so we don't have the data there. And after that, he goes on and lists all these restrictive assumptions that we have to go through. And again, we have to do them because we do not have coverage of the sun. So if we have full coverage of the sun, first of all, the first point will be totally irrelevant because the data will be available from wherever, from all of these viewpoints. But on top of that, you do not have to make any of these assumptions at all. And the better thing is, at any given time, you will have synoptic maps in near real time. So you can drive your model dynamically. You do not have to resort to these steady state models anymore. So basically, the takeaway from this is that single viewpoint observations cannot provide a comprehensive view to address the long-standing knowledge gaps in heliophysics. And for that, obviously, it goes without saying that we need a new approach to observe the sun and how it shapes its environment, that is the heliosphere. And that's where, okay. That's actually where a concept like Firefly, which is the new name for the 4Pi mission, comes in. The 4Pi, Firefly mission is basically a constellation of 4 spacecrafts. 2 of them will launch and start drifting ahead and be behind Earth like Stereo did, like Stereo is still doing. But the novel thing is, at a certain point, we can actually park these 2 spacecrafts that will start orbiting the sun at the same rate as Earth. So these 2 spacecrafts, together with Earth, will provide 75% coverage of the total surface area of the sun. Now, we supplement this by 1 or 2 spacecrafts that will go all the way out to Jupiter to get a gravity assist to get out of the ecliptic. And after that, what we do, we start circularizing the orbit. And at a certain point, we will have a configuration. For this study, we did it 2-to-1, that is perihelion at 1 AU and aphelion at 2 AU, but actually you can continue circularizing the orbit if you want to get it almost near circular. Anyway, once the constellation reaches its final orbit, at any given point, you will have over 90% coverage of the total surface of the area of the sun. And at any given time, we are observing both poles only for brief moments when we have just a view of one pole. But there is no time when we are missing both poles at all. So this is the good thing about Firefly. So, and this is the science that we want to do. There is another point that I wanted to make. One of the challenges that we have to deal with is the coupling between the different systems that we have in the heliosphere, between the solar interior, the solar atmosphere, and the solar wind. These are evolving on special and time scales that are totally different. And ideally, to address this, you want simultaneous observations from almost identical instrumentation to avoid any issues with different instruments. So this is the science we want to do, is basically to understand the global structure and dynamics, of the sun's interior, the generation of solar magnetic fields, the origin of solar cycle, the causes of solar activity, and the structure and dynamics of the corona as it creates the heliosphere. And you might say, this is everything, and it is everything. And this is actually the main idea behind Firefly. So far, we have been modest in launching missions that will provide incremental science. I think now we have to learn some lessons from the other communities, like the planetary community, like astrophysics community. Be exciting in your science, and that you will attract the agencies, the sponsors, the public, everybody out there. So this is our science. Basically, I said it already, our science go from the solar interior all the way to the solar wind. And this is near simultaneous observations from 3 or 4 viewpoints all at the same time. And it goes for a solar cycle. That's actually the prime phase of the mission. It's a whole solar cycle. But this data is not, oh my goodness, how can it go back? Okay. But this data is not only good for us, in the heliosphere community. It can actually be so useful for other communities, like in the magnetosphere, like the ionosphere, even people who are doing with stellar physics and habitability and small bodies. So it's a comprehensive data set that will serve at least over 60% of our community, but it will serve also the other communities out there in the heliosphere. So once, as I said before, once the constellation reaches its final orbit, at any given point, we will have at least 90% coverage of the total surface of the sun. Compare that to 25% from a single viewpoint. That is basically, I mean, like day and night. Continuity. So the data will be streaming 24/7 for years. There is absolutely no interruption whatsoever. We will be streaming data all the time. I mean, observing continuously. Comprehensiveness, obviously, and you will see it on the next slide when I talk about the payload. The data set that a constellation like Firefly provides is probably the most comprehensive data set that we will ever see in the heliosphere. And obviously, unity. Here we are unifying basically the whole community together to work on these challenging problems. And that's actually something we need so badly to work together. And I'll come to this point later. There is a slide I want to point to it. Oh my goodness, I'm going too fast. Anyway, so for the payload. This is the payload that we considered for the study. but this is just the study. The final, if NASA decides to go ahead with the mission, then the payload has to be thought about again. And obviously, we have remote sensing instruments, but also we have in situ instruments. For some of these instruments, they have to be all over the place. They have to be on all the spacecrafts. And the prime example is the vector Doppler magnetographs. And the reason for this, and they go back again, that you have to have exactly the same instrumentation on all the spacecrafts to avoid any cross-calibration issues later on. Same thing, we have also the EUV imagers, irradiance instrumentation. We have white light imaging, coronagraphs, and heliospheric imagers. We have also a whole suite of solar wind in situ measurements, like magnetometers, like Faraday caps, composition of solar wind in energetic particles, and obviously we will have the energetic particles suite as well. But let me say this. First of all, a suite like this is so complement each other so nicely, and it's so diverse, but the most important thing about this is flexibility in the payload. Here we considered only this set, but for the real mission, you can play all sorts of games with diversifying the payload. Some instruments, you don't need them all over the place. For example, if you take spectroscopy that is missing here, we don't need spectroscopy from all 4 viewpoints. You can just have it on 1 or 2 of them. Same thing if X-ray imaging. You don't need it on all spacecrafts. If I go to composition, similar thing. In a way, what I'm trying to say here is that you can play all sorts of games to have even more comprehensive payload for the constellation. The other thing also that is so nice about this, it basically builds an industry around our science. For example, if I go to one institution for the classic missions, we usually, we build one instrument. For this one, you have to build multiple instruments in the same time. And if I take, for example, back in the US, when I talk about industry, I'm thinking in the US, but it's valid everywhere, is the fact that when you have money going into different places of the country, you will have political support. Because the politicians want money to go to their districts and where they are getting the votes from. And that's actually that's actually what the planetary folks are doing, and the astrophysics folks are doing. We are not doing that. I think we have to start thinking about those lines as well. Another piece of the, is not listed in the table there, but it's in the lower bullet there, modeling. Modeling is actually part of the payload. And what we are thinking for the constellation is modeling has to be funded from the get-go, like really like an instrument suite. And the reason for this is we are bringing a new data set that we did not was not available to us before. And the existing models probably will not be, cannot work with it. For example, if you take the data-driven models, like MHD models of the corona and the heliosphere, the current models cannot digest this type of data. So the models has to be modified, changed, and probably redeveloped to be adapted to this data stream. And that's why we are arguing that the modeling from the get-go has to be funded as a suite. And this is the nice thing about Unity as well that I mentioned about this earlier. So here we are talking about 4 spacecrafts or 3 as a DISCO, and we are talking about dozens of instruments. That's actually where multiple agencies can be part of this. We don't need to build the whole constellation with one agency like NASA or ESA, but everybody can have a piece of it, and everybody can be part of this mission. That's actually what we need so badly. And I go back again to the astrophysics and the planetary communities. They are way more unified than us. We have to be so ambitious and so also exciting in our science to excite everybody, our sponsors to be part of this. I was talking to colleagues here, and they said, well, I asked them about their prospects for the future. Every one of them say, yeah, it doesn't really look that very good because missions are getting expensive and this and that and whatever. I told them, well, if you have really an exciting mission and you want just build a piece of it, they said, yeah, we can actually, that's really great idea. We can do that. And that's actually will alleviate the burden on everybody. Let me point something here about this mission. And oftentimes it's a question that comes. Okay, you have 4 spacecrafts that you have to operate exactly in the same time. And the operation for a constellation like this one will be challenging. And the data return, actually we can do it, but the more data is better. The nice thing about Firefly, you can actually decouple the ecliptic from the polar spacecrafts. The ecliptic has to be identical, the polar have to be identical as well. And actually you can build them in 2 different places, 2 different agencies or whatever, you can think of that. And even in operations, you can operate them in 2 different networks. For example, you can operate the polar on the DSN, the US Deep Space Network, and you can operate the ecliptic on the European network. And that's, again, it pushes toward this unity, toward collaboration altogether. I have an advertisement later, so I'm saving a minute for it. But I'm going to leave you with the movie I showed earlier of the constellation, and I'm happy to answer any question if you have any. Thank you so much.
Thank you very much, Noor. Questions?
Do you want to ask your question? You can go first.
Thank you. Very interesting presentation. And I have more practical questions. So when mission achieve final configuration, how long you will able to observe whole sun? Because, with such problems, it is really critical.
Okay, that's really a great question. So let me say this. For the in situ measurements right away, you don't have to wait at all. For the ecliptic spacecrafts, they are operation a month after we launch. So those are like stereo, exactly like stereo. For the polar, actually you can operate them remote. I'm talking about remote sensing here. You can, when you are far away, you can do observation, but the observation are not very useful when you are too far from the sun. But once you get close to the sun, you can observe. The only time, and actually we are still thinking about it, when you are firing the engines to circularize the orbit, initially we thought that probably, yeah, we will have too much jitter on the spacecrafts that will not allow us to observe. But actually, now we are thinking, actually, no, because the engines we considered for the study were not really the ideal ones. There is actually a new generation of engines that give a lot of stability to the spacecraft, and then you can observe. But typically, it's about 3 years after that you will start observing continuously. And as I said before, it's a whole solar cycle.
For whole solar cycle.
But that's a prime mission.
Okay.
If you extend it, then yes.
Hi, Noor. Thank you for the talk. That was really great and very exciting. One of the things that I have often thought about in terms of the magnetic field, so looking at the sun in this 4-pi form, the magnetograms that we would get would be very informative to the boundary conditions of the MHD models. Is that enough? Do we need to start thinking about looking at the coronal magnetic field in the corona and kind of thinking about, this mission being kind of a really good, I guess, filling in a really good gap to what we need to do, but also thinking about, like Sarah was saying today, thinking about instruments like Cosmo and start to look at more of the global magnetic field in the corona.
No, absolutely. That's really, when I talked earlier about the flexibility in the payload, that's actually the sorts of opportunities that a mission like this one gives you. Maybe for the coronal magnetic field, you don't need the instruments all over the place, but certainly you can have them in one or the other. So that's definitely, there is room for that, and that is what is great about a mission like Firefly. Let me another, because this is in a way kind of high risk, high reward, but there are a lot of high risk, high reward science that we can do. And another example, which is, I think we tried it with Soho, we were not very successful. I would say we were not successful, is the G modes. Firefly will give you the room to have an instrument or two to finally answer that questions whether the G modes are there or not. So there is room for this high risk, high reward science, definitely, like the coronal field, like G modes and other science. Absolutely. Yeah.
Another great mission, of course. I don't have a question, only a suggestion, which is, you know, this coronagraph, you know what I'm about to say, of course. Just put hydrogen, Lyman alpha. I mean, METIS has demonstrated that in terms of mass, power, etc., you can have two channels in one instrument. And the the possibility of measuring the solar wind outside of the flatland that Sarah was talking about this morning would really be a big improvement, a big a breakthrough type of science, I think.
And no, I totally agree with you, and that goes back to a point I made.
That's a Stroman payload. It's you know, we went through the same with the solar orbiter. Initially, the Stroman was visible. Actually, was you know, kind of leap of faith to include also the Lyman alpha hydrogen. Still demonstrated that it works from an instrumental point of view, and also above all from a science point of view.
Absolutely, and as you just said it, I mean, we have so great examples from previous missions and great instrumentation, and that's actually for the mission like Firefly, you don't need any developments. You can actually do it with existing technology that we already have, like the coronagraph.
Location, right?
There you go.
Hello. Yeah, incredibly exciting mission. I hope it does fly. But one question I do have is about particle acceleration, shock waves, and so on. And a key diagnostic of those is the radio emission that comes from those. And when I look at some previous studies, even done with Ulysses, they triangulate things, they can work out where shocks are. But with this configuration, you'd actually be able to do it in 3 dimensions and relate it to a CME. But I didn't see any radio instruments in the payload. Am I correct?
Well, yeah, I think there is a reason for that. As I said before, this payload, we just consider it for the study. And by the way, the study, we only have $300,000, and we have 6 months to do the whole thing. So if the Decatur recommends the mission and NASA goes ahead with it, so what will happen is there will be a science and technology definition team that have to have a deeper study of the mission and then decide what is the payload. And the payload will be basically open. I mean, will be open to every suggestion. And then I believe if multiple agencies are going to be part of it, there will be some negotiation between the agencies. Who's going to do what?
Yeah, that's great to hear. Okay, thanks.
Yeah.
Yeah, great presentation. My understanding is that the 4 spacecraft are quite similar to each other in terms of their build. You showed that they're not going to have some of them, they're not going to have all the instruments that other are going to have. You explained why. Just out of curiosity, why not include them in the other spacecraft too, just for redundancy? Is it a cost reason or?
It's cost, it's schedule, it is a lot of, and actually some of the measurements, honestly, you don't need them everywhere. That's one. And the other reason I would go for it, instead of having, let's say, 4 composition instruments, I'm taking composition here as an example. It's not really that what I'm thinking. Instead of taking 4 composition instruments, all 4 spacecraft, I would probably have 2 and have 2 other different instruments like spectroscopy or something like that. That will give me more science to do. So and after all, I think that's a debate that we have to have once we decide to go with the mission. That's something we have to talk about. Yeah. Can I do my advertisement? So my advertisement has nothing to do with Firefly. I talked a little bit about the superstorm that we have in May 2024. And we are organizing a workshop that focus on that week or week and a half of high solar activity and its impact on the Earth environment. So the workshop will be from October 28th to, yeah, there are 2/28th, one of them has to drop. October 28th to November 1st, it will be at APL, but it will be also virtual hybrid. So there will be a virtual component to it. What we want to do for this workshop is basically bring the whole community from the sun all the way to the Earth environment, all in the same place, and try to focus on these events. What went on the sun? What is their impact on Earth? What we learned from it? What are the things that we do not still understand, and what we should do in the future? So that's the website to register and submit abstracts if you want to. And by the way, we are also part of topical collection that includes geophysical research, JGR, GRL, space weather, and there is a fourth one. Which one is the fourth one? I forgot. I think it's Earth Science. So you can submit your papers to any of this, but at the end they will be collected also all in the topical issue. If you need more information about this, you can either go to the website or send me an email. I'm happy to send you all that. Thank you very much.
Thank you. Our next talk is by Den Yuan Yong, and we stay with missions that want to see the solar poles because he will introduce us to the Solar Polar Orbit Observatory, SPO.
Hello everyone, I'm Yuan Yong from National Astronomical Observatory of China. So I'm glad to have a chance to introduce the Chinese solar polar mission. We call it SPO. Okay, it has a Chinese name from the center of Ming Dynasty, but I do not have time to explain it. Okay. Which one? This one. Okay. So, okay, the motivation, but as a researcher of solar physics and space physics, we all know the motivation for the solar polar detection. And this morning, Sarah gave a good overview. But for a presentation, I have to repeat it again. So, okay, so the polar region of a celestial body are very important to understand the internal physics and to understand the external environment. In Earth, the polar expedition has lasted more than 200 years and get a good input to the model of Earth's climate change. And in the past decade, there are many spacecraft to the Mars, to the Jupiter, and to the Saturn. We get many magic observation, and we know, by this observation, we know the internal of this planet. However, as the host star of our Earth, we do not know the polar region of the Sun, not well. Okay, so no, how come? Okay, so it doesn't matter. And as a Sun, so the solar polar region is very important to understand the internal of the internal structure and the dynamic, and also we know the polar open magnetic flux and the high-speed solar wind is very important to the hemisphere, and especially important to our space weather of near Earth. So however, up to 2020, okay, then almost all the imaging to the Sun is on the ecliptic planes. So when on the ecliptic plane to observe to observe the solar pole, it almost similar to observe the solar limb. So when we observe the solar limb, so what happened is here, I gave an example, it's a magnetogram of HMI. So from the eastern limb and the center and the western limb. So we see what happened. So in the limb, the poor spatial resolution and the poor magnetic sensitivity, and even there are many mixture of polarity. You even don't know if they are true or just pseudo. So if we want to have high quality operation with magnetic field of solar polar region, you have to go to above the solar polar region and carry out the face-to-face observation. So the history, we all know this. So Unisys made a great progress in space science, but however, Unisys is a large eccentricity orbiter, so it has limited observation time to the solar polar region. And the most important, Unisys do not have imaging instrument to the sun. And 30 years after Unisys, we have solar orbiter, and the solar orbiter is the first time to escape the ecliptic plane to observe the sun. However, the inclination angle is not large enough. It's still side looking to the solar polar region. So after solar orbiter, to go to above the solar polar is a natural choice. So that's so the scientific objective of SPO. So okay, everyone knows this, but I have to repeat again. So the first objective to understand what drives the solar magnetic cycles. So it's a big science for solar physics and space physics, but the dynamo model can explain the solar cycle well. But okay, so but the model is perfect, but there are many observations about solar polar region is not clear. For example, we found some strong magnetic dipole in polar region, and Herode observed many small scale activity in polar region. So because of we do not have high quality observation of magnetic field, we do not know this. So our dilemma, the current dilemma cannot explain this. And for the solar internal structure and the dynamic, because we do not have good observation of Dopplergram in the solar polar region, we cannot know this global heliosysmology and the deep convection zones. So we hope SPO will reveal the generation mechanism of the poloidal field, and we hope the SPO can clarify the location of the toroidal field. So that's the first. The second objective is about the high-speed solar wind. It is also a big question in space science. So where the high-speed wind comes from? Is from the inner plume or interplume? So we don't know. And what's the driven mechanism? It's magnetic connection or wave. So it's not clear. So for this question, it's because we observe this high-speed solar wind on the ecliptic plane. So it's will interfered by the force bound of the middle and low latitude solar wind. So we can hardly to get the original information or high-speed solar wind from the coronal hole. So the second, because we do not have a good magnetic observation, it is not clear. So if the magnetic reconnection and or wave is the main mechanism, or both of them are. So we don't know. So we hope SPO will determine the source location and its fine structure, and we hope to quantize the contribution of the mechanism, which one, and which, how much, which, also something like this. So, and the third objective is to study the spatial area of the hemisphere. To study the spatial area of hemisphere, so MHD modeling is the most effective ways. But for the data-driven MHD model of hemispheres, you need the global distribution of magnetic field. Okay. So, however, everyone knows the open flux problem, because at this moment we do not have the good operation in the solar polar region, so we cannot resolve the problem of open flux problem. So we hope SPO will reveal the global distribution of solar magnetic field, and we want to know the 3D structure and the propagation process of the solar wind. So, I guess, in addition, this main objective, the SPO can do more science. For example, coordinate with other ground-based space projects. SPO can give the 3D images. We call it, we can go the so-called cloud map of spatial area. So this model is given by our young colleague here. So, and we want to know the distribution of solar radiation with different latitude. Okay, the payload of SPO. SPO will equip 7 kinds of payload. The first is the magnetograph to provide the vector magnetic field and the Dopplergram, and the second is EUV imaging and integrated spectrograph. And we have a coronagraph with white light and polarization observation. We have a very large angle coronagraph. You may call it hemispheric images. So white light and polarization. And we have X-ray image, and we have no frequencies, radio spectrometer, and plasma wave analyzer. We have 3 kinds of in situ detection package. It's for the ion, and for the particle, and for the in situ magnetic field. So the payload, this payload, okay, is a typical solar satellite, and the satellite will provide 200 kilogram and 430 watt for the payload. And we hope the lifetime is 15 years, but it's hard to do. So we say it's 80 years mission and extend 7 years. So the orbiter is a small intrinsic orbiter, and in the mission time, it's 3 years orbiter, and in the extend, it's reached the 1.5 orbiter. And the important time for SPO is it needs 3 years to reach the Jupiter, and by GAGA, SPO will enter its solar polar orbiter, and after 2 years, it will force to reach the solar polar region above 55 degrees. So the schedule, SPO with some other space science satellite is undergoing the final evaluation of our national neighbors, and we hope it can be finished before this end of the year. So, although it's not officially approved, but SPO have been required by our Chinese Academy of Sciences to start this project from the beginning of this year. So that's all. Thank you. And any suggestions, comments, and what kind of collaboration are will welcome. So thank you.
Thank you very much. Are there any questions? Yeah, I have a question myself. I may have missed it in the last slide. What is the status of the project now? I mean, what would be the idea for
this year? Yeah, yeah.
Or when would the launch be planned?
2009. 2029.
29.
29, yeah, between the January and the February.
Okay. Okay. Any other questions? Thank you then.
Okay.
So then let's move to the last speaker of this part before the posters, who is Naryaki Nita, who will present us the benefits of multi-point observations of the sun. Yeah, this is the one to go to the next slide, and this is the pointer, and we want to leave 3 minutes for.
Okay. Yeah. When I submit an abstract, I try to present some highlights of stereo observations, but instead I just refer you to the senior review proposals that are available at the Stereo Science Center website. And on that proposal, you would see those, the scientific emphasis was really dependent on where the stereo was. I just show what the coverage of the stereo observation was during the whole mission. And when 6 months after the launch, it was just like this. A and B still very close to Sun-Earth line. And when SDO was launched, it was already like this. And full coverage, 360 degrees coverage continues until stereo B was lost in October 2014. And then the eastern part, this is the Stonyhurst presentation. So the center is central meridian, and the edge is the west 180 and east 180. So anyway, eastern hemisphere was missed. Then stereo B, stereo A passed the superior conjunction. The western part was missing, and that gap was enlarging. And then it passed the Sun-Earth line last year, and we are like this now. So I first want to remind you that extreme event occurred in 2012 like this. And very big magnetic field and very fast solar wind, and the estimated DS index was like minus 1,000 nanotesla. And the reason was, when we mentioned, I was the co-author of this paper, and the reason that makes the Carrington, sub-Carrington class event was CME-CME interaction very close to sun. And then a low density solar wind due to a past CME. And then the associated flare was only X1, not X10 or X100. And I just explained why we thought that way. This is my paper, and I just used the one of the channels of corner channels of UVI. UVI 195 angstrom channel contains iron 24 line, which is sensitive to plasma like 50 million degrees. And that this AIA also has that channel 193. So the correlation between GOES and that channel is like this. So when the flare is intense, the correlation quite good. So using this relation, we came up with a Gauss X-ray intensity of this event like X1. So now I'm pretty interested in what is called the corona dimming. Corona dimming is a very good indicator of corona mass ejections. And back in Yoko days, 1990s, our friend, this guy, classified corona dimmings like various things. But it was not clear what he meant about, especially in relation with corona mass ejection. But after SOHO and now SDO, we have on the stereo, of course, and we have a better control of understanding of what the dimming means, especially in terms of core dimming or secondary dimming with respect to corona mass ejections. But still, it's a ongoing project. I try to, I have a kind of a bias about maybe there are different kinds of solar eruptions. One is maybe instability dominated, and another one is reconnection dominated. I want to tell the difference by using the signature of dimmings. So I just picked up the really different properties of corona dimmings in 12 dimmings observed on disk by AISDO and on the limb by stereo EVI. And I just tried to locate this disk dimming in terms of the height projected on the limb. This is just still ongoing project. But then stop this, and then there is a big effort about modeling the CME 3D structure, and also shockwave on top of that, and using the famous GCS model and the ellipsoid model like this, and developed by these people, Ruyan Kwon and Alexei Ruyal. This is very important, especially in combination with MHD simulations. They are steady state simulations. They can derive the shock parameters, and they're very useful for SCP investigations. But I just remind you that this event is still mystery. This is what is called a circumsolar SCP event, observed at very wide longitude. And especially at Earth is here, and the source region is 60 degrees behind the limb. Still very fast rise of this SCP flux. And some people like SCP person like Eric Posner seems to think that there is a secondary eruption to account for the SCP at Earth. That's not a possibility, I'm sorry. This is just one eruption. And so this is still a mysterious event. And I want to say that EUV observation shows that this flare, associated flare, was just like a two ribbon flare. And the EUVI 3 or 4 angstrom images suggest that the magnetic field is quite weak. And CME speed was only 900 kilometers per second. And this one shows the EUV wave, and connection to Earth is here. The wave doesn't really come to this. That's okay, but still, I'm saying that this is not very big eruption. And then going to stealth CMEs, I just say stealth CME because it depends on the instrument. If we have an infinite sensitive instrument, maybe there is no stealth CME, but still there are events, CMEs, but no clear on-disk corner signatures that can be geo-effective. And I'm just proud to say that I co-organized the ISI meeting and recruited young people like Stephanie here, yeah, Stephanie and Erica, and four young people, all female. It's very good for diversity inclusion. And I actually, we're also responsible for a live event for some of the team members. But anyway, so these papers are produced, and just to remind you, some of the events were observed that the different phases of stereo orbit, and just telling you that stereo was very important for solidifying the source, identifying source regions. For example, this one, the clear ICME here, and the only CME that was responsible for this ICME was this very, very slow, 100 kilometers per second or something like that CME. And where's the source region of this one? It's very hard to know. But if you look at different long delta T difference image, then you see some dimming here. And it looks like expanded corner hole expanding. But how is it connected to this CME? You really need a side view to confirm that this can be totally far side event, maybe. I don't know. So you need some stereo observation. At this time, there was no stereo observation, 2015. So, but then, this is a really problem event. And ICME here, there was no CME in a reasonable time, halo CME. And there will be some dimming here, but no CME corresponding to this dimming. And that we try to find CME, and only marginal thing with this stereo A observation. But I don't think we got a consensus of all the team members. So it's very unclear because at that time, stereo was very close to the opposite of Earth-Sun line. So it didn't really provide the independent view of the CME. But this one was helped by stereo. This way, LASCO was very, CME was very diffuse in LASCO. And of course, there was some rather clear film interruption, but it was not really clear how this evolved. And only with stereo observation, there was some CME1, CME2. And so this was, I just wanted to show that stereo was very helpful understanding this event. But lastly, I want to just say, this is my personal message. And you want to coverage mission. And so top priority to me is a magnetograph, really magnetograph, because it helps you validate your MHD models. MHD model is very important because in the heliosphere, most parts will not be observed at all. So very sparsely sampled. So so it's very important to validate those models. You see, you want to say lots of beautiful science for coverage mission, but my main emphasis is this. You really need to validate your MHD models. In order to do that, you need a very good coverage magnetic field of observation. And then there's a question about maybe put your satellite at the fixed point, L4, L5 or something like that, or orbiting. I just made this movie, something like this. So I just want to see 8 sets of stereo launched 2 years apart. So it looks like this. So I prefer this architecture than just put small number of satellites in a fixed place. And with this, you can calibrate your instruments better, or also derive your vector magnetograph from line of sight measurements. I think you may say that vector magnetograph is very important, but it's very hard to analyze. Yeah, very hard to analyze. It's you have IQUV. Often I and V are well observed. That make line of sight magnetic field information, but QU are often giving you just noise. So I actually really prefer putting many satellites and have a longitudinal magnetograph. And the keyword is very lightweight and laser calm. And this also applies to polar mission. So thank you.
Thank you very much, Nariaki. Are there questions? We have time for one question. If not, you can still find Nariaki, of course, during the coffee break and poster session. So then we will, let's first thank Nariaki again and also the other speakers of the session. And then we will have posters first. And I understood also a special event at the Indian booth at the fair. So let's resume later after the posters.
let's get started. All right, welcome back. We're going to now complete session 6, which is lessons learned and future developments toward a 4-pi view of the sun. And our very first speaker of this last session is Don Hassler, who will be talking about the Solaris mission, a focused solar polar view from outside the ecliptic plane. All right, Don.
Okay, look at this crowd, full house. Marco, what's the roundtable later on? Am I involved in that? No. Okay. Okay. All right. Okay. All right. Got it. Okay. Can everybody hear me? So let's see, the presentations just before the break and Sarah's presentation this morning starting off the day. It's been an exciting day. It's been a good focus on out of the ecliptic and off the Sun-Earth line studies of missions. I think that's where we want to go in the future. Sarah laid the groundwork for a lot of the exciting science that we want to and can do, and then the mission design studies. There were 2 exciting missions that were talked about. I think the motivation for Solaris, which is a focused mission to go over the poles, is we really want to fly. We want to fly something soon. We want to fly it while Solar Orbiter and Solar Probe are flying, and we also feel that the science questions are compelling and urgent. And I think that and I'll mention this later on, but in a way, you start with a small mission and you do the big one. You don't always just go straight to the big one. So in the case of imaging, for example, there was TRACE, a small CubeSat or small-sat kind of a mission, and then later on down the road they did SDO. They did the full, complete major mission. Or in the case of IMAP, IBEX was a small mission, and then they did a bigger mission. IMAP. Run the mic. It's too loud. Got it. Right. So I'm going to skip this slide because I think I just kind of said that. But Solaris, we started working on Solaris back in 2019 as a mid-X proposal, as a focused mid-X proposal. Got category 1. We got a phase A study. We got $1.5 million from NASA to do a phase A study. We spent another $3.5 million of our own money since then. So we've worked on the Solaris mission concept to do something now, to do it quickly and to stay focused so we can actually get it done. We spent about $5 million, and we've been working on it for about 4 years. We really didn't have any weaknesses. I think there were programmatic balance issues within heliophysics at NASA, and that's politics. I don't want to talk about that. But we're also, everybody's waiting for the decadal survey, which is going to come up shortly, sometime this fall. So the idea here is, what is the highest priority? Let's try to get over the poles quickly. Let's do this science quickly. I think a constellation is going to be phenomenal. That's ultimately where we want to go, but we want to get over the poles. We have questions that we need to answer so that we can move on to the next step. How does the solar cycle work? That's a huge question, right? That's a big question. How does the solar dynamo, which actually drives the solar cycle, how does that work? Well, you have to go over the poles to answer these questions. And we believe that a mission like Solaris, one single spacecraft over the poles, can answer these questions. The orbit, similar to what others had shown earlier, you get to get out of the ecliptic. Ultimately, you have to go out to Jupiter to do a gravity assist. We come back in, we use gravity assist at Venus to circularize the orbit, to slow the orbit down, and you get multiple orbits. You can get an orbit a pass over the poles every 3 years. If you had 2 spacecraft, you could get one going over the north and one going over the south every 3 years. But basically the idea is you circularize your orbit, and you could go for a whole solar cycle, getting 3 or 4 passes over the course of a solar cycle. A solar polar mission similar to a solar probe. Someone mentioned earlier, solar probe was, it took 50 years to make solar probe happen. They were doing studies back in the 60s and 70s to do solar probe. Similarly, with the solar polar mission, it's been over 50 years there too. I mean, the Interstellar Solar Polar Mission, ISPM, was working. It was 2 spacecraft, an in situ spacecraft with which ultimately became Ulysses, and then the remote sensing spacecraft, which got canceled. So we need to complete that mission. We thought it had to be a flagship mission until now, but we showed with Solaris, with the very detailed study that we did, that we can do it quickly and inexpensively. So understanding how the dynamo works, the mechanisms of the dynamo. Dynamo is a fundamental process. It's extremely important, and this is the primary objective. I think that, if you're going to try to do a mission quickly and focus on, one primary objective, understanding the dynamo, constraining the dynamo mechanism, that's it. Also the advantage, and Sarah talked about this morning, getting out of the ecliptic plane. You have this, kind of fried egg, sunny side up view of the sun and the heliosphere. So if there's a coronal mass ejection, it doesn't matter which way it goes, you're going to see it because you're up out over the poles. And this will be very informative in terms of space weather research, but also understanding the dynamics. Sarah talked about, you have a coronal mass ejection and it interacts with the rest of the solar wind. And what, where does it, how does it interact? And how does the physics work when you have these events? And in fact, there's been a lot of talks today about solar particle events, and they can have a span of 180 degrees or not. And understanding that physics is extremely important. So the 3 flows that Sarah talked about this morning, as well as the magnetic field, there's fundamental questions that we actually absolutely have to go over the poles to measure. We can't measure them from the ecliptic plane, but fully understanding differential rotation, global convection, meridional circulation. Meridional circulation is really key in terms of understanding, potentially validating the Babcock-Layton model of the dynamo and the length of the solar cycle, or even the magnitude of the solar cycle. It's not exactly 11 years, as Sarah said this morning. It's shorter, it's longer, it's bigger, it's smaller. All these questions are fundamental questions, and you can make measurements with a single spacecraft mission such as Solaris to answer these questions and constrain those models. What's unique? Solar Orbiter is flying, and we want to fly while Solar Orbiter is still up. Solar Orbiter will get out of the ecliptic. We're having our first gravitational assist very soon, I think, in November, and we're going to a little bit later on, but but we're going to slowly work our way up to higher latitude, 17 degrees latitude, and then ultimately 30 degrees latitude. But it's still relatively a small snapshot. It's a relatively short snapshot from what we'll get from Solar Orbiter. I think 32 degrees is the maximum latitude that we'll get with Solar Orbiter. It'll give us our first glimpses of the poles, and so I think it's going to be phenomenal. But to get to greater than 70 degrees, you get a longer duration, over 100 days of views of not just the poles, but the entire polar crown. And it's the interaction of the polar crown and all that structure and dynamics in that entire area. You need to be able to observe that for long enough to watch the evolution of those structures. And those structures, those giant cells, typically have lifetimes on the order of 2 or 3 rotations. So we need to get a sustained, I think Nor talked about it, everyone, we've been talking about it all day long, having this sustained view. So I think Sarah showed this video this morning. This is a simulation that we produced as a part of our study for Solaris. And, you can see the polar crown is the dashed line, and this is the amount of time, the number of rotations that you get to observe this. The simulation on the right basically shows the number of days that you have a view of the entire polar crown. And, you get a glimpse of it with Solar Orbiter, but, if you have a mission that gives you 3 months, contiguous 3 months over the poles, you get to see the whole polar crown for basically over 100 days. And so you get, if you have two spacecraft, you get to do this at each pole at the same time. But one spacecraft will get, you get this view, this rotational view of the sun of each pole, fundamentally within just a couple months of each other. For a focused mission, we don't need to Christmas tree it up. I mean, we certainly can if we want. If we want to go big, let's go big, and we can have full remote sensing and in situ instruments. But if we want to focus on understanding the dynamo and having a focused mission that we can do now while Solar Orbiter and Parker Solar Probe are flying, we need a Doppler magnetograph, and it can be a line of sight magnetograph. It doesn't have to be vector. Most of the fields on at the poles are relatively more or less radial. And plus you get, because you're going quickly, you can actually recreate the three-dimensional structure as you go. An EUV imager, of course, and you want to overlap that EUV imager with a coronagraph. So, and then, it doesn't cost too much to have a magnetometer. So you can get magnetic field measurements from this too. So you'd have these three remote sensing instruments and a magnetometer. And I think the really cool thing about trying to fly this quickly is, this polar mission, Noor talked about it, Sarah talked about it, is really the cornerstone for constellation mission down the road. We've had assets at L1, we've had stereo go all around the sun, and we've had them at stereo's been at L4 and L5, and it's been on the far side. Stereo's been doing this effectively with two spacecraft plus L1. The one spacecraft we don't have to complete this constellation, the cornerstone that we need is this polar mission. So, in a way, in an aggregated sort of way, which is this international approach, which Nora referenced and Sarah talked about, we, leveraging international participation and contributions in an aggregated way, we can produce, we are producing, in fact, this 4-pi constellation. At L1, we already have assets at L1 and SDO. Space Weather Next and SWIFO, these will be missions which have perfectly, good science capable instruments. L5 Vigil, that's a European mission. It's going to be at L5, and the science capability of both C-Core, PMI, and JEDI. PMI is the magnetograph. JEDI is the EUV imager. JEDI has overlapping fields of view out to 6 solar radii, easily overlapping with the C-Core. And so, we're going to have a science quality mission, even though it's labeled a space weather mission at L5. Oops, sorry, I want to go back. Yeah, the Koreans are very excited at COSPAR a couple of weeks ago. The Koreans were very excited about doing a mission at L4. So, and they want to launch in a similar time frame. They need contributions, but we can outfit that mission with similar types of instruments. So really the last remaining spacecraft to outfit is this polar mission. And so if we can fly this at the same time that these other assets are going, Vigil launching in 2031, but Solar Orbiter and Parker Solar Probe are up there now. And, we can do this small mission as a pathfinder, like TRACE went to SDO, IBEX went to IMAP, and we can do it now. And, kind of in summary, and I think everyone's kind of showed these slides, we had no idea what we were expecting to see when we went with Cassini or Juno over the poles of Jupiter and Saturn. And there were phenomenal discoveries to be had. So we expect to have similar types of discoveries with whatever spacecraft flies and the first spacecrafts that fly over high latitude poles of the sun. Thank you.
Thank you, Don. And we have time for a couple questions.
Hey, Don. Great talk. Thank you. So I had a question about resolution. So I've heard now a couple of people talk about going over the poles and being beyond 1 AU. Is resolution an issue when taking these measurements of the poles in terms of magnetograms?
No. Fundamentally, you design your instrument for the distance you're going to be operating from. So if the primary operation range for Solaris, for example, is 0.9 to 2.5 AU, you design it to give you the resolution you need. The instruments we are baselining would be MDI-like resolution for magnetograms, And, you know, these don't have to be, you got to stay focused on what the mission is and what you need, what resolution you need to do the science you're trying to do. You know, we're not going to be a Parker Solar Probe and we're not going to be an SDO, but you can design your instruments for the resolution you need for the mission.
I guess compatible to what an MHD model would need to.
Oh, absolutely. Yeah, 100%.
What is the overhead of putting a vector magnetograph instead of line of sight? Is that too much, too heavy, or?
Well, the ones that exist that have TRL6 are twice the mass and twice the cost. So if you're and 4 times the telemetry. So if you're constrained in any of those resources, you know, you got to look at the value added. I mean, and this is a whole topic we could talk about for a long time, but the whole value added of doing, if you're doing polar science, do you really need to have a vector magnetograph? And you know, I don't want to start that whole conversation, but you got to look at the science objectives you want to answer.
NASA has a fatal mistake by not putting magnetograph on stereo.
Well, that's a whole different question. That was a question of not vector versus line of sight. That was a question of magnetograph versus zero. Thank you.
Our next speaker is Silvano Fineschi, who will be talking about the upcoming age of new space coronagraphs, perspectives for joint science with ASPICS, Codex, and METIS.
Thank you, Sarah. Good afternoon. Yes, I would like to mention a few possibilities for joint science with METIS on solar orbiter, Codex on the space station, and ASPICS on the Proba 3 mission. I'm with the METIS team. The PI for Codex is Jeff Newmark and Andrei Zukov for ASPICS. So we have heard about, you know, missions in the 2030s, but the 20s really are the roaring 20s for coronagraphy. And it keeps going. I mean, I would like to talk about possibilities for missions, especially Proba and IS Codex that will be launched, one Codex in October and November Proba 3. I will focus on these two and not Punch because there is a strong Italian contribution for these two missions. And of course, METIS, which is an Italian experiment. Here I've overlapped the field of view for Codex. So it's a wide field of view, ASPICS. And of course, what you're looking at is the METIS field of view. Across from the beginning of the mission, this is the visible light channel. I will talk more about this. And here you see this zooming effect as, you know, solar orbiter gets closer to the sun. Actually, the field of view of METIS will span both field of view for ASPICS, very close to the limb, basically a sort of artificial eclipse, and Codex, much wider. The just for those, maybe too much, no? Okay, well, sorry. The coronagraph for solar orbiter is a two-channel, but one telescope with a beam splitter for the UV, Lyman alpha hydrogen, and the visible light polarized. And these are the type of images you get from METIS, the H Lyman alpha 1216, and the broadband center around 500 nanometers for the polarized K corona. So from these two products, one can derive the outflow velocities of protons, hydrogen really, through these diagnostics, the Doppler dimming. Basically, you have the coronal line that as the coronal atom flies away from the chromosphere, it gets out of tune spectroscopically from the chromospheric Lyman alpha. And so the intensity drops, there is a dimming, and from the observed intensity, by knowing the electron density from the visible light polarized brightness of the K corona, one can derive the outflow velocity. There is, though, an important physical parameter that needs to be known, is the coronal electron temperature, because basically goes into the ionization balance. The intensity, of course, depends also on how many neutrals you have in your emitting line. So just to give you an example of our work that has span across half cycle. Here you see the, for the minimum, close to the minimum, the raising phase and the maximum right now. The Metis observations in visible polarized brightness, the H Lyman alpha. From these images, you get the coronal electron density. And these are the maps of the outflow velocity for protons, electrons. So here you see the slow wind in the streamer belt and the fast wind on the polar coronal holes. And as the solar cycle increases, you have fast and slow wind all over the places. Here, though, as I said, was assumed 1 million degree electron temperature. If you assume, for instance, a more realistic temperature profile, for instance, Sarah's temperature profile, you see that you still don't make a big difference. You don't have a big difference during the maximum or rising, but still when you have a well-structured streamer belts or polar holes, probably because we are looking to this line effect, a line of sight effect, you may be wrong of a few 100 kilometers per second. So all I'm saying is that the Doppler dimming, don't get me wrong, the Doppler dimming technique with Metis works. You get nice with a reasonable temperature profile, but of course, the Doppler dimming diagnostics would benefit from an independent measurement of coronal electron temperature. So who's going to come to the help? And this is the coronal diagnostics experiment. It's an experiment that will be launched on a SpaceX in October. Actually, it was supposed to be launched in September, but because now Falcon X will be used to go rescue the astronaut stranded on the ISS, has been postponed to October. And this is combined simultaneous electron density, temperature, and velocity measurements. The PI is Jeff Newmark from Goddard, with the contribution of CASI, the Korean Astronomy Space Institution, and ENAF. I won't go into the detail. What you want to remember is, of course, the field of view is quite wide. And you have 4 filters besides the broadband, and the detector is a polarization image sensor. Italy contributed with the ground calibration and, of course, science analysis. This is, this is a codex in our facility in Turin. And how it works. This is actually diagnostics that was discussed in 76 by Cram. Is the you have the Fraunhofer photospheric profile that gets smeared out by the thermal broadening of the K corona, the electrons in the corona. And in the deep valley of the H and K calcium line, you still have, the K corona is not so K, it's not so continuum. The reason why it took almost 50 years and more is that you need a very good radiometry, the order of percent that at that time was not possible. So here is how it works. You have 4 filters, 2 center on the nodes that are insensitive to the electron temperature, and the other 2 center on the concave and convex parts of the spectrum. And this is an example of the prototype that flew on a balloon of the corona in these 4 filters. And so the idea, what's the idea? The idea is to have the data from METIS together with the data in the 4 bands, wavelength bands of codecs. You derive the solar wind speed assuming a reasonable electron temperature. And you actually derive the electron temperature assuming it's weakly dependent on the wind speed still. And so the challenge is to combine these 2 measurements to pin down electron temperature and outflow velocity. As an example, here we have done some simulations. Basically, from the PB measurements, polarized brightness, we derive the electron density. Assuming the conservation of momentum and mass following Lemaire and Stegen, we derive a temperature profile, and we create a electron temperature map. And we feed this map to create these synthetic 4 images. You see the very tiny difference between one filter and the other. So it requires a very accurate radiometry. And then we derive from the ratio of the ratio of these images, we derive the temperature map. Basically, we know the electron density, and we change the temperature and the velocity until we match the observed ratio. And when we compare that with the synthetic, the assumed temperature is not that bad. So the combined METIS CODEX diagnostics would provide, this is what we get using the reasonable electron temperature profile, which is kind of quite different, especially for the minimum, assuming just a rough value all across the corona. Opportunities, the opportunity we are talking about now meaning next year in April, there will be an alignment, inferior conjunction. This is solar orbiter, this is Earth. And by then, hopefully, with CODEX and METIS, we will test these combined diagnostics. Very quickly, I go to this other mission. Again, what I mentioned before as a perspective, combined joint science between CODEX and METIS is just an example. Like also here, I just make you aware of this wonderful possibility of this mission launch in November. Italy contributes with the formation flying metrology and ground and in-flight calibration and the narrowband pass filters. So it's a very eccentric orbit because only at the apogee will be achieved formation flying. Formation flying, this is the orbit. So this is it's a 1 day, 20 hours orbit. And during these 6 hours, you will have formation flying. We are talking about 150 meter separation with 1 millimeter and arc seconds precision in the relative transverse relative position. So you will have every day for 6 hours an eclipse-like type of observation. So here again, you will be able to go down to 1.1 solar radii, quite high cadence. You have all sorts of science objectives, the waves, of course, coronal structure, different scales. So the point is that finally you will get, this gap, observational gap between the limb and the usual inner field of view of coronagraphs. Slow solar wind, CME progenitor, the initiation of CMEs, and so origin and early acceleration, origin of coronal shock waves. Show you if it works. Yes. These are waves from density fluctuations from stereo core 2, and these are visible light difference measurements with a 20 seconds cadence. And we see all these density fluctuation. And again, it would be interesting to see what happens down to the limb. And I conclude just giving a different perspective from the usual field of view. If you think of the beta parameter ratio between the gas pressure and the magnetic pressure as a function of height, the METIS observes really the transition magnetic region. And ASPIX goes from where the magnetic field dominates to where the magnetic field dominates towards where the thermal pressure dominates. And then you have a nice overlap with codex all the way up to 10 solar radii. And this overlap, as I said, is, on one side, wind, on the other side, you have the electron temperature. And I stop here, just leaving you the summary with these bullets. Thank you for your attention.
Thank you, Silvano, but unfortunately, we don't have time for a question. I'm sorry. But we'll have more discussion later. Okay, moving on. Our next speaker is Jun Lin. Yes. And he will be speaking about solar close observations and proximity experiment scope mission concept. 2 minutes till the yellow turns to red.
All right. Okay, thank you. Yeah. Well, I can just use this one. Okay. Good afternoon, everyone. I'm glad here to have a chance to introduce my mission called Solar Close Observations and Proximity Experiments. And here's the content of my report. And first of all, what we should do, we just send a spacecraft into the solar atmosphere as deep as 5 solar radii to the solar center and investigate the extremely hot and bright uninhabited zone near the sun and perform in situ measurement of the magnetic field in the corona, including that in the polar region, and also perform very close observations on various magnetic structure and plasma distribution over large latitude range, and also traverse the CME and the CME flare current sheet on orbit of the perihelion at 5 solar radii. And why are we doing this one? Here just is kind of a description of the orbit this mission from launch to the to the Jupiter flyby and Jupiter Sun orbit drift, and then just decrease the aphelion and also the perihelion by the electric rocket. And here the science of scope is firstly is just try to solve the puzzle of solar eruption, and the second one is solve the puzzle of coronal heating, and the third one is realize breakthrough in obtaining the key physical information. Since March 11th, 1960, we already have more than 70 satellites in the orbit, and these are the satellites that are still working now, and most of them are around the elliptic plane and around the Earth orbit. And then Solar Orbiter got the inclination of orbit about 25 to 34, and the perihelion of 60 solar radii, and the aphelion of 302.4 solar radii. And here is the PSP with the inclination is very small, but very close to the sun. Is kind of in situ measurement of the sun for the first time. And here is the solar pole observatory, which has been introduced by my colleague Yuan Yong earlier today. And so what's the significance of the scope, which is first of all, we just try to solve why the solar eruption occurs. Back to 2000, Terry and I developed this model, which has been confirmed by lots of observations and numerical experiments in many aspects. But in some in situ measurements of several key structures are still lacking. Some important questions are still open, like the scale of the current sheet. According to the classical theory, the thickness of a current sheet is only 100 meters, but observations indicate that the thickness of the current sheet could be up to 10,000 kilometers. And numerical simulations indicate that the turbulence and the associated small-scale structure in the current sheet account for the faster dissipation and the thick current sheet. And also because the most of the energetic stage of the solar eruption occurs in the range less than 10 solar radii, and it's a very complex physical phenomenon due to the coupling of many processes: magnetic field annihilation and heating, and the acceleration of plasma and emission in various wavelengths. But the limitation, the intrinsic limitation to the remote sensing is that we just all deduce the physical features of objects only according to the radiation. The second goal of the scope is to solve one of the 8 major puzzles of astronomy: coronal heating and solar wind acceleration, a mysterious phenomenon such that the cooker is hotter than the oven has challenged the solar physics community for about a century. And now we have 2 candidates of mechanism. One is MHD wave, and another one is nano flare. And both are just need the very, very high resolution observations. Here's the nano flare, which indicate that it maybe occurs in a scale less than 10% arc-second in scale, and the initiation of the MHD wave in the football on the photosphere is less than 40 kilometers. And it's heated corona expands outward, developing into the solar wind, and which is the key issue that govern the interplanetary space in both time and space globally. And it undergoes very apparent acceleration in the region below 10 solar radii. And the third goal is the magnetic field in the corona. The energy driving the eruption is stored in the corona magnetic field beforehand. The more complex the magnetic field is, the more energy could be stored. And the fine structure of the coronal magnetic field is essential for energy storage. But we are still lack understanding of the coronal magnetic field and its fine structure because of lacking universal methods and technique of routine measurements of the coronal magnetic field. So here we just list some specific cases that for the special situation that we can obtain the information about the magnetic field in the corona. And the scope will perform the in-situ measurement of the magnetic field in the corona at altitude lower than 10 solar radii for the first time in the human's history, and also observe directly the polar region at a distance less than 6 solar radii for the first time as well. And what's this is comparison of the scope and the PSP. Of course, PSP is the pioneer of the deep space mission of the solar physics, and is of great significance, and it is a very fruitful mission. Now we are promoting a mission that works in a different fashion. Here, just to give the comparison of the orbit parameters of the scope and the PSP. And obviously, scope was also a mission close to the sun, but will be closer than PSP and at a apparently large inclination of the orbit, and which can cover a large range of latitude. And here is just a summarize of this comparison, which got the closest approach to the sun and a higher orbit inclination, broader latitude coverage, and ultra high resolution, and finally we got a comprehensive sensor information. And payload, we propose 3 payload as detect of mid-high energy particles, which to in-situ measurement of various energetic particles and explore freezing of the charge state of heavy ion in the solar wind. And second one is the electromagnetometer for in-situ measurement of CME current sheet and the shock, and the in-situ measurement of the coronal magnetic field, and also explore the dust-free zone and recognize the inner boundary of the dust disk in the solar system. And the third one is a multi-wavelength spectroscopic imager. They got the wrong version, which is a remote sensing stuff working at the 5 wavelengths is 171, 193, 94, and 304, and 5300 angstrom. It's just macroscopic observations of the eruptive configuration and nanoscale structures, and also the magnetic field in corona and including the polar region. So the technology we will involve is a 6 part of the technology. Now for the time being, we're just working on these 3 basic technologies. One is light thermal insulation material technology, high temperature thermal resistivity coating technology, and the cooling and the power supply integrating technology. Here is just we're talking about the light thermal shield coated with material of high radiation resistivity. Here is the main body of the thermal shield. It's very thin, not very thin, 30 centimeter, and the interior is filled with the carbon foam, and the surface, and the surface facing the sun is coated with 3 layers of rare earth material. And here at the back of the thermal shield, we attach a thermoelectric conversion unit, which used to cooling the system and then create the power. Why we were doing this doing this way is because there's near the sun, the heat is a big problem. For the PSP, it's every watt of electricity generated by the solar panel will produce the 13 watts of heat. So if we still use traditional solar panel for scope, they were just facing about 50 watts of heat when we generate 1 watt of electricity. So now we just use proposed to use the dual power supply system when the satellite, when the spacecraft, when the spacecraft is far from the sun, we use the traditional solar panel. And when the spacecraft is very close to the sun, we use it's a thermoelectric power supply system. And this kind of technology actually is widely used in many deep space mission. But in that case, just usually they use isotope reactor as a thermal source. For the scope, we have the sun has a huge thermal source, so we just directly use this heat to create the almost done to create the power, to supply power. And okay, and finally this we said this scope will enter the uninhibited zone near the sun and provide us unprecedented information about the CME, flare current sheet, large scale magnetic reconnection, and so on. And the aims is to solving 2 puzzles and realizing 1 breakthrough and something more. And before I end my talk, I just give the advertisement of our journal called Astronomical Techniques and the Instrument. Is special, it's just a very focusing journal for the techniques and the instruments, also the data processing and the AI for astronomy as well. And finally, we just tell everyone that we have many openings in our observatory, and any applications are very welcome. Thank you very much.
Thank you so much. Okay, we have time for a couple questions. Questions? Yeah, come up to the microphone.
So that's quite a mission you're planning.
Yeah.
My question is about the remote sensing instrument. That's also quite a demanding one with many different wavelengths. And I think you wanted to observe also magnetic fields.
Yes. Here, let me answer the question first. This one is the remote sensing instrument. We just working on the 5 wavelength. 197, 170, 193, and the 94, 304, and the 5300. And the style we cannot use directly see the sun. We use a kind of periscope type structure. Use the diamond to collect the light into this main body of the telescope. And
do you get rid of most of the heat?
Yes, for the diamond, the diamond is very good. It's very transparency to all those emissions with wavelength longer than 3,000 angstrom, but could be up to 80% of the visible light can go through here. And here again, we have another transparency diamond here. So finally, when the energy get into this area, this main body of the telescope is only about maybe I think less than 1% of the, or maybe I don't exactly remember how much, but very low. Can be make sure that the instruments in this part can work properly.
Thank you.
Yeah, thank you.
Thank you.
Yeah.
Thank you, speaker again. All right, our final speaker is Dipankar Banerjee. Here. And he will be speaking about coordinated observing plans for Aditya L1 and other space platforms.
Thank you. If it is a cricket match, I'm the last batsman to bat. There is a stadium close by. So let me try to give you again a very quick overview or a recap of the Aditya talk, which my colleague, Dr. Shankar Subramaniam, we are co-chairing the science working group. So hopefully we'll get some insight about this. Just to remind you that this is the first of its kind multi-payload observatory class mission. We have multi-wavelength coverage. We have optical, we have X-ray, we have infrared, and the particle detector. So it's a combination of 4 remote sensing and 3 in situ observations. So we are looking at source and also its effect at the L1. So there are many different, questions can be addressed depending on the, instrument capabilities and so on. Just a very quick summary, probably this basically summarizes my talk. Launched September 23, insertion was January 24. The PV phase is over for all the payloads except the coronagraph. We still have some issues with the coronagraph. We have a little more scattered light as we expected. The guaranteed phase started. This is basically for the people who build the instrument. So there are hardware components came from different institutions. So the guaranteed phase started for most of the instruments, again, apart from the coronagraph. We have just completed 1 hello orbit last month. Early 2025, I think this is most important for this community. We hope that there will be announcement of opportunity expected for joint observation. So this will be a real opening to the global community. Having said that, I would like to remind you that all the instrument PIs are already coordinating with other, instruments and other space platform. I will show you some examples. So if you are interested to have a joint observation, please contact the PI. It is possible. There has been joint observations with solar orbiters. There have been a very regular observation with other missions as well. So please do contact. We can make you connect with those, in particular. Again, very, very quick thing that, we have this coronagraph with 4 channels. Incidentally, the green channel is really, really performing pretty well. The other channels have some issues. We are addressing it. Suit covers the first time near UV full disk, images. And this is also performing pretty well. Both the particle detectors are, performing very well. I will not show much results, but, Shankar has shown. Both the X-ray spectrometers, the low energy and the high energy also is performing very well. They have joint observation with sticks, and the results are very, very promising, as I understand. And even the magnetometer, we were not very sure about the cleanliness of the satellite, but we have 2 probes in an extended boom, and that differential measurement is allowing us to get a reasonable handle on this. As I said, I will not talk about too much on the coronagraph. Shankar showed about the green light images. I will just show again a very quick wrap of the some of the suit instruments, because that's often quite promising. This is the website. You can contact Durgesh, is the PI, many of you know. And Sami is also one of the science collaborator for this. I think we are now looking forward to have more science on that. The status, payload was switched on even before the insertion. That's actually interesting. We were having discussions today. Even before we reach the final orbit, these days, the stability of the satellites are reasonable to start observing. And we were pleasantly surprised. It was not planned, but just our space agency said you can start observing. So the first light was even 1 month before the insertion in the L1. Insertion was there. PV phase is all completed, as I indicated. Pipeline is ready. Science data is all going into ISSDC. So this is our data center for all ISRO missions, and I will show where it is, and all the time even allocation committee is already constituted. So the proposal submission system is also handled by ISSDC. This is a very much follow-up of our own astronomy mission called AstroSat, which is in 7th year of operation, and international community can submit proposals in AstroSat. So similarly, we expect this will come. So that was the first slide, as I indicated. This is one particular event which I like to highlight. which Soot has seen the other day. This movie was not working, so you could see an eruption. You could see some part of the loop. You could see some kink motions. So this is quite promising magnesium observations. And I would say that with probably the Chinese Lyman alpha or even METIS, we could target some of these things to target. There's again another last May event. I think Sarah can even remind today morning what you show after the eruption. You have the formations of these again little structures here. So these are again seen by magnesium. So that I think has a lot of capability in terms of studying this kind of even after eruption restructuring and so on. There are many different filters. So this is Durgesh sent me this slide. So this is already a campaign with the solar orbiter has been taking place. And as you can see, there are multiple filters. We have also broadband filter. This is primarily for atmospheric, science community to work on. Just a very quick reminder that the coronagraph has a multi-slit option. So this is our field of view, and we have multi-slit. So when we are actually doing a raster scan, it is actually taking pretty reasonable time. So we are able to get a raster full image within 10 minutes or so. So that's actually quite promising. Since we have the continuum, you are asking this, we are able to, really get a reasonable handle on the quality. So there are lots of, possibilities of different. I will again advertise a little bit of punch here. With NFI, our idea was to have, a real good observing campaign because Aditya just fills the gap. So again, the inner corona, we are all seen that how, less observations we do have. So we are looking forward to this future prospects. So please do, this is again, Dan created this BV. And you could see very clearly the field of view of SUVI, Soot, then the coronagraph, the white light channel. The green channel is only looking up to 1.5, but we have a very good spatial resolution with 1.5 solar radii. Of course, Aspix is also there in the same field of view. So I think we need to identify, because Aspix also has 6 hours of observing period. So this will be the opportunity to find out the windows, and then we will have dedicated, because Aditya is going to work more of a proposal mode thing apart from its synoptic observation. So we'll try to design the proposal mode. Shankar and we both are in the time allocation committee also, which has been constituted. So we hope that we will be able to do quite a bit of staff together. Just to again highlight the spatial occasions, and we should probably do not miss this kind of opportunity when the conjunctions come. So I am trying to list out this. As I said, March 24 is already gone, but 25, we should not miss this opportunity. Again, the same field of view. This is again another very good opportunity of conjunction, September 25. As I again indicated from January, since we will be trying to open up, even as I said, if such great opportunities come, we can do it even tomorrow. Those opportunities will be there with the special request to the time allocation committee, which is already in place. Another, again, repetition of what was also highlighted by previous speaker here. PSP conjunction, I think this is again Whisper with this change of field of view. I think the movie is not playing. In situ, I think there is a huge opportunity. They have already, I was told, they're really comparing with Discover and Aditya and all the already L1 payloads. So cross calibrations are happening. There are people, the team. If you are interested, as I indicated again, you can contact the PIs. Even if it is not open, it is possible to collaborate. That's what I was told. In situ, there are just I found out this, that maybe what the magnetospheric people did earlier, like MMS constellation near Earth. I don't know whether such exercise has been really done. So this is almost like a kinetic scale physics, magnetic reconnection, closer look. Since near L1 we have multiple such things, if such modeling efforts. So this is just a projection of what we can do. I just saw Christian Mostel is doing quite a bit of very nice work. He just hired my former student now. So I'm looking forward to have these kind of, our own students participating in major international programs and taking Aditya data to the next level. Again, a bit of advertisement for Punch. Thankfully, I'm also part of the team. I just want to indicate that for this particular mission, this is first of its kind, ISRO has formed a support cell. The idea is that solar physics is not so popular across the country. So we are going around the country to train the next generation students from the MSc level. So these are master students. So what we do is we have already had 7 such workshops. That's what we do. We get young people, have a little interaction, expose them with this, and we go around in a different part of the country. And later on, we will have these schools open for international students also. The next school actually it is in next month. We will be focused on in situ data analysis. So all the PIs will bring in their data and will sit with the students. So that's the way we are moving forward. I indicated earlier, and again repeating, that all the data, science data, goes back to this main data center. So even if you submit a proposal, you have to download the data from ISSDC, not from any PI institution. Even now it is the process, and there will be a proposal submission system which will be available here, which I indicated it is there for other space missions from ISRO, and the same principle we will be following. That's my last slide. You are most welcome to visit me. This is the view, you can have it from my office. And thank you for your attention.
Thank you so much, Tapankar, and we do have time for some questions.
Great talk. I am interested in the data products associated with the in situ observations. So I did see that you can measure both protons and helium. Is there going to be a data product for both?
Yes, Shankar is here. You can connect also with the PI instrument. This is the Physical Research Laboratory who is providing that. So Dibyendu Chakrabarti is the PI. Yeah, Shankar, you want to comment more?
Yes, I mean, it will have both proton, electrons, as well as the heavier ions, including hydrogen and helium. One of their objective is to look at this ratio of helium to hydrogen.
Okay, that was my next question. Will we have heavy ions as well? So heavier than helium?
There are few, I mean, hydrogen and helium, we are able to cleanly separate, but there is an instrument called PAPA, which looks at the heavier ions. And so far, we have not seen much from that instrument. So that is one possibility that we can use that for the heavier ions.
Is that for the thermal population? Or is that energetic particles?
This is for the non-thermal, I mean the strahl and other components.
Okay.
The other interesting thing about this, the aspects, the particle detector is it has a directional capability. Shankar pointed this out. It has multiple things. So it looks at the Parker spiral arm and also away from it and all that. So by, sort of some modeling, you can get a global sort of view of the particle trajectories and so on, connecting with the source. That's the idea.
Great. Thank you.
Any other questions? I have a question for your joint observing proposals that you're talking about. What kind of lead time will people need to make such a proposal?
Yeah, I would say about 3 months, probably. So we are looking at that cycle. But again, if there is some kind of special opportunities, the time allocation committee can sit and approve that even within few months, like the target of opportunity, what the other astronomy community uses. So those provisions are there. I think 10% of the time is actually for such global campaign mode observation. So that campaign mode observation, even last minute can be adjusted.
Other questions? Not, let's thank Tapankar again. Okay, thanks so much. And indeed, it's the Roaring 20s. This is really exciting to see all of this. At this point, I'm going to turn this over to Marco, who's going to chair this last section of this meeting.
Okay, we had about 25 minutes to finish. I would like to just to summarize. There is the presentation to summarize what we've done in this symposium, and there are a few people that might add something, especially about future missions. I didn't write anything, so I have some impressions. So the idea that I put a lot of effort to put together this symposium. Of course, we didn't have much time to have everybody speaking. So the symposium was trying to put together both the science on the sun and the heliosphere, but also the space weather, and also talk about future missions. So regarding the science, there were a lot of abstract applied. And the impression I had is that we are still, especially for the remote sensing instruments, we are still working on the old missions. So the new missions, talking about Solar Orbiter, I'm talking about Aditya and ASOS. It takes a little while to people to understand how the instruments work. Maybe there is a lot of tuning up, of calibration to be done. So I think the science will come later on these missions. The in situ are more standard data, so it's easier to start using them. Regarding the space weather, the space weather and science sometimes are conflicting. Science needs spectroscopies, needs high temporal resolution, high spatial resolution, and high polarimetric capabilities. Space weather needs, especially to be operative, needs real-time data, so quick data that for a quick reaction. But they have to talk each other, because in order to tune the algorithms that are needed for the space weather, for the warnings, you need to have data that come from science missions at the beginning. Regarding the artificial intelligence, we received not many abstracts. So it means that it's still starting this discipline. And I see that young people are more capable to start working on these things. Anyway, I think it's a growing thing, and it's important because the data are really a lot. So we need also not only humans, but also artificial intelligence in order to take out science out of this data. Talking about future missions, we had several contributions. We had very nice future missions. They are very ambitious. And I think the main objective looks like to be the polar missions. So looking at the sun's poles. So there are, and one important thing is to have magnetographs that will be capable to measure the magnetic field in the photosphere at 4 pi, so in all parts of the sun. I think it will take time to have these missions up and running. So far we have to go on with our missions. Talking about, for example, SOHO, LASCO is still working, and people are worried what happens when LASCO will be shut off, because most of the images relative to the corona come from LASCO still. So regarding the future missions, I have some, to move on is the big green. Okay, I received some input. Maybe I will call people to talk very quickly. I have at the last thing I have Lika Guatacurta, who is connected. Can you hear me?
Yes.
No.
I'm here.
Oh, you're okay. So I leave you the floor at the end of this time. So I got some input from Li Feng, adding a little bit more about Chinese missions. So we heard about SPO. we heard about scope. And then beyond the big solar missions, there are small space mission interested in high spatial resolution in UV or the soft X-rays, or for example, something like a spectrochronograph, which is missing since the time of UVCS. Then I would like to call Dipankar to say something. He gave me a couple of slides. So if you want to add something more with respect to what you already said. No, the slides are here. Yeah,
okay. Yeah, so Aditya is big for India, but then the community started, talking to each other to see what is beyond Aditya L1. We did a vision document. So this was an exercise which was done from the Astronomical Society of India. We are trying to sort of coordinate the space and the ground together. There is a ground-based, long-pending 2-meter class telescope proposal waiting for funding. So the discussions were now also, should we, again, you pointed this out, whether we really delineate space weather. Because what is happening, it appears that from the government side, this is suddenly has become a reality. And from our defense, from our other agencies, they want to have a dedicated space weather mission. So we scientists may be given an opportunity suddenly that you have this satellite or you have this space in some other thing. So our readiness is required. So we looked at, whether we could take that opportunity and use our scientific interest along with the sort of, service requirement. So that decision is coming, and we were sort of asked to get into a sort of compact coronagraph kind of design, compact magnetograph design, and this doesn't exist in India yet. So this could be an opportunity for even international participation. But again, frankly, in India, our agency wants the instrument, the hardware to be built in the country so that, it really helps in the community building. The other thing is that there is a strong magnetospheric and planetary working group as well. So whether we could combine certain missions in that way. I saw pleasantly that we had, again, the priority, small versus big. Are we looking for, again, like after solar orbiter, should we wait for another 20 years to 10 years to get a big mission, or we should have a readiness to get much smaller? As I just, you mentioned about the Chinese approach, that along with the big ones, you should have a small ones. But we all agree in terms of either L4, L5. We missed the bus actually for L5. There was an opportunity given to us for L5, but we were not ready for that. Space weather study from different vantage point, out of elliptic polar observations. Of course, we are all thinking probably in the same line. But I think I liked Noor's statement also. I think it is high time that we talk to each other and then approach the agency. It is possible. I just indicated that, India is part of TMT, 30-meter telescope project. India is part of square kilometer array. India is part of LIGO. So these are all really much higher value item, products. Even ISRO is partnering with JAXA, and the next lunar mission of Japan, JAXA, the lander is going to be provided by India. So this is possible, but it needs a lot of buildup of the community to come together and get it to the our agency. And I think it may not be impossible. So again, it comes to the question whether you go for really high resolution, high spectroscopic mode observation versus coronal field again with new techniques. We're talking about apart from Zeeman effect, whether we go to the second solar spectrum. But it appears that if we all want more or less a similar kind of suite of instrument, either a imager and a heliospheric thing, magnetograph from as many locations as you see. So I think independently, again, we will not be able to do a justice to any of this list. So it is, I think, high time that we start talking other and try to fill up each other's gap. So that's my message here again. Yeah, thanks.
Noor, you want to add something? You give me slides, something different from for pi. Yeah, okay. No, okay. So Zami also had some impressions and then I'll give the floor to Lika. She will talk about artificial intelligence. Okay. No,
I don't have slides. I don't have slides. It's just going to be 2 minutes. So we have heard of many new missions coming, and there are 2 missions which are similar to things that we have heard of today, which will very likely, one is coming and the other is coming very likely. The first is the L5 mission, Vigil of ESA, which in some ways is going to be similar to one of the spacecraft on Firefly. It will have a range of instruments, both optical, chronograph, heliospheric imager. There'll be a magnetograph, and EUV imager is now clear as well, and in situ instruments. And there are very concrete plans. These are very recent. They were made public at COSPAR just 3 weeks ago, that South Korea is going to build an L4 mission, which will carry basically the same instruments. Actually, they have a few more than what Vigil has, but it hasn't gone through the D-scope exercise yet, right? So my guess is in the end, it will end up with about the same, but at the moment, it's even more ambitious. It goes to L4, and I think that makes it extremely exciting because you get 2/3 of the angular coverage of the sun if you have L4 and L5. And if you also have something in L1 or in Earth orbit, you're really getting a lot. Now I know that our chair would love to have coronal magnetic field capabilities in there, as yet they're not yet there, unfortunately. But yeah, I think that will need bigger instruments than these. Sorry? From the ground, yes, definitely. But it would be good to have 2 angles for that as well. And so that's the positive part. I do have one worry. We heard about high resolution. We've heard about extremely high resolution, very close to the sun. It'll be extremely challenging. Even from solar orbiter, it turns out to be very challenging. We are going to get at least 2 very high resolution coronal missions. There will be Solar C with EUVST. There's also MUSE. And although it's getting old now, IRIS is still also working. So all these are at the sub-arc second, sub-half arc second scale. Except for Hinode SP, we don't have anything in space with similar resolution for the magnetic field. No, I'm wrong. Of course, there is SOFI on Solar Orbiter. How could I forget that? But it's looking at the sun from different directions. It's not, going to be there all the time to support these instruments. And Hinode is getting slowly old, right? 18th birthday around there. So I think we need to worry that we will have very high resolution from the corona, but we will be missing magnetic field of similar resolution. You can do it from the ground in theory, but anyone who has tried to observe from the ground and has seen how conditions change and how variable they are, you cannot build on that. You cannot build on that. So I think that's something that's really missing and we should be thinking of and pushing. So I've taken enough of your time.
Lika, are you still there?
I'm still here. Are you going to play do the slides for me?
Yeah, I will. Let me skip these ones. Okay, you tell me when to go. Sorry.
That's not my slide.
No, that's not.
That's Noor's.
That's too, I went too far. Wait. This is the first one, I think. This one is the first one.
This is not my, these are not my slides.
It says Lika. I can skip this one. This is what you sent me. Is this yours?
Yes. So, okay. So I don't know where the first slide went. I was seeing Firefly.
In what I'm showing and what you are going to see.
This is, no. This is not mine.
I think probably it would be better if you show your presentation from Zoom.
I will try because I'm on a government computer. I'm not sure that I can share, but let me see. Otherwise, I can just speak to it.
Because there is a very long delay between. Try.
Let me try. I'm not sure that you are seeing my screen. Are you?
Not yet. Here it's coming.
Okay.
Yeah.
You're able to see?
Yeah, now we see many slides. You should go.
Okay. Well, I'll just go quickly. I do not even wasn't planning to share, so
okay.
I think you should be able to see. So I think Marco, you put together a fabulous session. I listened to the plenary talk by Sarah, who really kind of captured a lot of the essence of what we are observationally gathering, but also, how we are trying to bridge our understanding, especially of the magnetic sun. But your challenge to me was kind of, how do we get this 4-pi view of the sun? Given all the exciting missions, they are still going to take a lot of time. But I don't think we should sit idle in the meantime, because we have data already collected from multiple vantage points, and we are still continuing that. And we can begin to utilize artificial intelligence and machine learning in that context. And so at NASA, over the last 8 years, we have invested, quite a bit of resources to literally kind of start taking hold of our data and see what we can do towards that. And I will end with a demonstration of this 4-pi view of the sun, which is really pretty mind-blowing. And you might have already seen a full-up presentation from Robert Jarolim, who was part of this activity at the Frontier Development Lab. So very quickly, we sort of really depend on the Heliophysics System Observatory. And these are not just NASA missions. These are NASA missions in cooperation with other agencies. And even if there is no cooperation, I think it would behoove us not to integrate them in future. And there are so many new ones. I was blown away by the scope concept. And June, good to see you after a long time, at least on line. And so, we create visuals to actually show where the spacecraft are. This is not, up to date. And so we have to add in here, Aditya L1, Future Vigil, Punch, as they come on, as you can see. But this gives a good perspective to people, where our data are, what kind of data, and how we might be able to begin to integrate them. This is another kind of key problem we have, scale of data. Without going into details, you can see that our data situation is overwhelming. We have actually created something called HDRL, Heliophysics Data Research Library. Just SDO alone has, currently 8.7 petabytes of compressed AIA images. Uncompressed, this would be 20 petabytes. Google tells us that if we were to host the entire 4K by 4K data of SDO on GCP, it's going to be their second largest data volume. That's saying something. And so we are collecting roughly 2 gigabytes of data every 15 seconds from over 100, operating missions. And this is from all divisions. And this is why we do missions. Now, do we get to analyze all these missions? Not really, not at the level our current research funding exists, and it's not at the level that our human brain can process this volume of data. And that's where artificial intelligence really comes into play. And what you're seeing here, I've given you a sample of the different kinds of activities we have undertaken in this summer program that we carry out every year for over last 8 years. And I'll give you some quick examples. So what you're looking at is really the grand challenge was, can we create a homogeneous set of magnetograms? We have taken data over 50 years from numerous observatories and also space-based missions. But there is high level of inhomogeneities between surveys which do not allow us as scientists to combine this data set into a homogeneous set for more sophisticated applications. And so the question was, can we do something with AI? And the answer is yes. We actually were able to create a homogeneous and super resolved map from about these 50 years of inhomogeneous observations that I talked about. And this is just an example. You are seeing where the input data is SOHO MDI. And, our goal is to really get SOHO MDI to HMI resolution. And that's what we succeeded. This is output, this is target, and this is the ML output. And if you want to learn more, I have a poster. You can look at the poster for a little bit more details, but this is already beginning to show what is possible. Have we kind of looked at the entire data set? No, we concentrated on active region. But remember, these are work done in 8 weeks, and there are papers associated with it. And similarly, you can see there is GONG input, and then there is GONG ML output, which is super resolved to HMI scale. This is another very cool area. Can we create virtual instruments, predict extreme ultraviolet irradiance? So back in 2014, Solar Dynamics Observatory, one of the sensors on Eve instrument malfunction, MEGSE, which was critical to giving us the irradiance that is really important for the ionospheric energy input. It's not F10.7, it is the MEGSE irradiance. And so what you're looking here is we kind of took the 9 filters from AIA, and you're seeing an overview, right, of ML architecture with SDO input on the left, and output is MEGSE spectral irradiance. Here, ML is used to compare basically how the sensors pass readings lined up with measurements from the observatory's other sensors, and then estimated what it would record where it's still running. Now, for this irradiance to work, we must have an operating AIA mission on SDO, and then we can actually extract the irradiance, which is pretty incredible. We didn't have to send an astronaut to space like Hubble to fix this. We have fixed our irradiance problem. And I show this because when we are thinking of future missions, we have to figure out how to make them efficient, and low power, low mass, data compression, all of these. And these AIA tools are teaching us a lot of that. This is the same data once we were able to generate the SDO ML data volume. What we could do, we can have derivative outcomes. We can auto-calibrate, cost-calibrate with onboard AI auto-calibration, resulting basically in resource efficiency. So with the machine learning data set from the SDO, what we did, we used the same data sets, these project identify spatial patterns on the sun to determine the calibration factor. We know that, right? That the EUV and UV will go through some kind of degradation. So what do you see on the left-hand side? The top arrow shows an overview of the degradation of 304 channel. It's recovered images and the architecture used. And the bottom row shows the comparison of real 211 angstrom channel and synthetic 211 channel, and you can hardly tell the difference. You can again take the same data, ML data, and utilize it for predicting thermospheric density, which actually was able to improve drag estimate. This thermospheric density prediction, very interesting, very important for space weather. When we compare them to models like JB08, NRLMCs, people who are actually using it for space weather, these models are actually better, completely data-driven, no physics in it. And finally, I want to go to the main highlight of this session that you put together, Marco, and that is how can we observe the sun and solar irradiance in this case from any perspective. It's 4Pi basically combines SDO, stereo A and stereo B when it was still available observations into a consistent 4Pi map of the sun. And remember, these observations are all in the ecliptic, yet we are able to get a 4Pi, meaning including polar view of EUV observations. This is a poster that was created when this work was finished in 2022. There is a paper associated with each of the areas that I have talked about, and the reference to the papers are in my poster. So while all these observations are obtained from the ecliptic, solar north, which is neural radiance fields, it's a mathematical tool, and ITI, instrument-to-instrument translation, because you're going from spacecraft to spacecraft, enabled a 4Pi view of the sun in EUV. And that's what the details are actually in the poster, but more details are in the paper. And if you can get hold of Robert Jarolim, please talk to him. And I'm going to end with this slide, which is what you're seeing, the sun as a fully resolved star. We've been able to successfully with AI/ML kind of create a 4Pi EUV view of the sun from SDO and stereo data. It predicts what the sun's UV emission images would look like from non-ecliptic viewpoints. Now, what we have to remember is as we are using input data to create this, we must have that input data to continue to create this. If we don't have that input data, then we cannot do this prediction. But the bottom line is we are using whatever we have, and we have more as they are coming in with our new missions, and we can be very creative about trying to answer some of our new questions. And some of the observations that you have presented at this meeting, and some of the observations that you still hope to get in future, is going to go a long ways with the utilization of tools like AI/ML in order to address many of our science questions. Thank you for giving me an opportunity to speak. Thanks.
Thank you, Lika. We have a few minutes before concluding. Any questions for Lika?
Actually, I have a question, not to Lika, but I have a
general. Okay.
Comments that I want to say. Lika, not for you, but in general. By the way, nice presentation. I like that machine learning. So one comment I want to make is that
something that you said at the beginning, research in space weather. Actually, there is a research in space weather as well. So it's like in the terrestrial weather. There is a research component. So we should be careful not to kind of.
No, yeah, probably.
Yeah, so
I didn't explain myself.
Space weather forecast, yes.
Yeah.
But there is research in that. Yeah. Then other thing that you said that, well, communities should worry about, Alaska, what would happen if Alaska goes away, right? Well, we have the same problem with magnetographs. So we have, on ground base, we have a GONG magnetogram and helioseismic measurements. Next year will be 30 years that instrument is operates, right? 30 years. HMI was operating for 15 years. Community should worry what would happen if these two instruments go away suddenly at the same time, right? What is the replacement? I think that's those two just comments, so not questions. Thank you.
Thank you. I have a comment about what Lika said of this reconstruction. It's to me, it's a little bit scary that you can reproduce the poles of the sun without observing really the poles of the sun. It's like trying to guess who's behind the door from sounds, from reflections. I mean, I have a probability that I can guess right, but not always is like this. You might create images which are not real, actually. Did you hear what I said?
Is the question for me or a comment?
Not comment, but
so actually, if you look at the math, that's why I said you need to get someone to kind of explain this, read the paper. If you see how this is done mathematically, I mean, when you think of 3D tomography, right, how we can take ultrasound and create a picture of the interior of the womb of a human being. So there are a lot of tools and techniques which kind of can be used if you have many views, multiple views, and that could be just in one plane. And so in case of stereo, we had basically two spacecraft going around. So between SDO and two stereo, when both stereo were available, there are many, many slices, right? And it's giving you a EUV reconstruction, not at the surface of the sun, but higher than the surface of the sun. It's wherever all of these lines are intersecting, basically. So it's not giving you magnetic field measurement. It is giving you, what UV irradiance would look like. UV irradiance doesn't give us magnetic field. But if we had observations of magnetic field, kind of like, say, if we had stereo and if we, with SDO, we could have constructed something perhaps. So these are just basic mathematical tools that is allowing us to reconstruct, project our data into this field. And I'd say that it's not artificial, it's augmented intelligence. We are using our tools that's available to us that other communities have used already and showing how we can begin to address this. Now we have to go through the process of validating that what we are reconstructing is correct. And one of the experiments we are doing in this year's FDL is looking at data that MAVEN has taken, right? Which is also measuring EUV, but from a very different vantage point, and see how well it combines with what this particular AI technique would give us. So we have to continuously do that. And I would say we shouldn't be afraid. We should try to validate, question, make it better. But this is a way to be able to literally take all our data and utilize it.
Yeah, thank you, Lik. And I didn't want to raise a problem now at the end of the. Robert was probably going to answer.
Like my reply would be probably in line with what Lika was saying. So thank you for that. We can also have a discussion afterwards about the individual details. But I really want to I want to highlight this aspect of it's an extended atmosphere. We are not trying to reconstruct like the photosphere. We are not looking behind basically the sun. That's not in there. It's like a time evolution. Plus, we also have a very good coverage at that time. So it was specifically picked in the way that we see it. Actually, if there would be a fraction that's like not covered, we would immediately, if the model would basically like escalate at that point, we would immediately notice it. So it's like, in that sense, it's kind of in this line, but anyways, it's, I'm happy to discuss it in more detail. And also, if you want to hear more technical details, the paper is also a good option.
Thank you, Robert.
Thank you.
Yeah, we will talk about that. Thank you. Sarah?
Yeah, just a quick couple comments there. First of all, I think this is incredibly impressive work. Couple things to bear in mind, as Robert says, there's a difference between trying to reconstruct the photosphere, which is not, if you think about it, the coronal limb, the poles are no different than the equator in terms of that you're going through a similar kind of structure, which allows them to do a reconstruction above the photosphere in a way that you couldn't do, for example, with a photospheric magnetic field. You couldn't do the same kind of thing. But something that's important to remember, any of us who have made synoptic Carrington maps from EUV observations know that you get a crystal clear image when you're looking on the disk and a smeary image when you're looking at the limb. It's just the nature of line of sight integrated structures. And as such, the measurement at the pole will have a disadvantage because in all the stuff at the equator, you also get to observe that structure as it rotates onto the disk when it has this clarity. So there's going to be a fundamental difference of resolution. I'd really like to understand better how that applies to this. But the fact that you can incorporate all this and make a polar view is really quite amazing. And I think it demonstrates that we can use these tools to pull together different spacecraft observations to really construct the 4-pi image.
And that's the whole point. I think we have to come to understand this and gain confidence and then begin utilization. Thank you.
Yes, I just wanted to mention the elephant in the room nobody talks about. Actually, there was some mentioning by Sami and by for Aditya. So sure, magnetograms from of the photospheric magnetic field are important, or high resolution. But what about the coronal magnetic field? I think that there is very little talk. There has been, at least. The punker mentioned Velk, but still, there is no in the plan or has not been discussed anything about that. You know, Zeeman, Hanle effect. In the beta plot I showed, you know, in corona is where the beta really moves from minus to +1, so it's highly dynamic, and it's an interplay between pressure, thermal pressure and magnetic pressure. So just wanted to, you know, ask people to think about, you know, possible missions addressing this long-standing physical parameter that has not been really measured directly.
So one of the standout features of this meeting for me has been the number of talks that is focused on missions beyond the Sun Earth line, out of ecliptic 4-pi constellation missions. The out of ecliptic missions, if you send one satellite or even two, they're not going to be able to look at the solar poles all the time because they're going to be moving pretty fast. In terms of constellation 4-pi, you need as many satellites as you would like. It seems to me that this is something that is ripe for international collaboration. And we have Alexei here, who is the is chair of the steering committee for the International Living with a Star program, which has been pretty dead for a while. Now we are at the IAU, which is supposed to kind of build capacity across nations. we have COSPER, we have ILWS. And I wonder whether we should take opportunity of this big excitement right now in, in the field about constellation missions, out of ecliptic missions, to bring together space agencies in a more organized manner, to send out satellites to look at the sun and space weather from various vantage points.
So since we've been talking about what is potentially missing to do the physics that we want to do, and maybe close on some of the big, long-standing heliophysics, solar science questions. So one of the things that is, to me, that is lacking is Alpha spectroscopy. So we have these wonderful measurements of temperature and ion temperature, electron temperature, different ions with UVCS. And that was so wonderful. And I go back, and actually the papers that I discussed on Tuesday have a component where we actually include those observations as constraints to show that the profiles that we were looking at that go into the heliosphere are actually compatible with measurements that we take of in the corona, as far away from the corona as we can, or as far away from the surface as we can. Is that something that people are thinking about? Incorporating into future missions? I think that's incredibly lacking right now.
Yeah, UVCS was a very complex instrument. Actually, there are plenty of data that nobody has looked at yet. So it's, I mean,
yeah,
if you
I
open
think
up the UVCS archive, you find a lot of things that probably were never looked at. So, but yes, I mean, this is one, actually it was mentioned by Lee, a spectro coronagraph that to explore other ions and temperature. Yes.
Spectrally resolved.
Anyway,
Yeah.
so it could be useful to have a discussion among people, international discussion, and try to understand it. If we can collaborate together in order to get more science out of these missions.
I think, with the advancement in technology as we are seeing, sort of putting occulter outside your telescope and all that, what UVCS once upon a time wanted to do, the next generation, basically. I don't think that the community that I know of has really gone back and looked at that in the light of today's capabilities that we have. And yeah, it was a very unique mission and worth going back and looking at what's possible today.
Okay, thank you, Lika. I think we are already over time. So okay, sorry, didn't see you. Yeah.
For those who would like to attend the Division E days, I don't know why they have changed the rooms that are in the labels there. They changed from 2.6 to 2.44, 2.46. So we are in 2.4 and not 2.6. So anyone who wants to come to the Division E days, go to 2.46. I will send the speakers who are here, several, the real room, but those who are public, if you want to attend, please, is 2.4 for 2.46. It's a room that it's two rooms in one room, okay? So I have just discovered in my cell phone that they have done this mess.
Okay, thank you. So I would like to conclude this symposium. So I thank you, everybody, for the participation, for being here, and for being connected.
Thank you. Bye.
I would also like to thank all the scientific organizing committee for making able to do the selection of the talks, and thank the organization for the smooth running of this symposium in this room. Thank you, everybody.